Do you believe that the strongest forces in the universe aren't just explosions and black holes? What if I told you that they are things that are so extreme that they can bend space, stop time, or even erase life itself? From old signs stronger than a billion suns to invisible jets moving close to the speed of light. This trip isn't just about the big, it's also about the impossible. Welcome to the dark side of cosmic power, where things don't always work out as planned, and the universe's true strength is shown. Gamma-ray bursts, the universe's most violent flashes. One thing that is so strong that it shines brighter than everything else in the universe put together and only lasts a short time. That's a gamma-ray burst, GRB. These are very short bursts of gamma radiation, which is the most powerful type of light. A lot of the time, they come from galaxies billions of light years away. For a short time, they shine brighter than any star, galaxy, supernova, or anything else. So what causes a gamma-ray burst? The most common kind happens when a massive star, way bigger than our Sun, runs out of fuel and collapses in on itself. But instead of just becoming a black hole quietly, this death creates jets of energy that shoot out from the poles of the star at nearly the speed of light. If Earth happens to be in the path of one of those jets, we detect it as a gamma-ray burst. There's another kind too. Sometimes two neutron stars, those incredibly dense leftovers from past supernovae, crash into each other. When that happens, it also sends out a GRB. These are called short-duration gamma-ray bursts because they last less than 2 seconds. But even in that blink of time, the explosion releases more energy than our Sun will give off in its entire 10 billion year life. What makes these bursts so mysterious is that they were only discovered in the late 1960s by accident. The United States had satellites in space to detect nuclear explosions during the Cold War. But instead of bombs, they saw flashes coming from deep space. It was the start of one of the greatest puzzles in astronomy. Gamma-ray bursts are not just powerful, they are also dangerous. If one were to happen close to Earth and be pointed right at us, it could cause massive damage to our atmosphere. It could strip away the ozone layer, allowing harmful radiation from the Sun to reach the surface. Some scientists even think that a GRB might have caused a mass extinction on Earth about 450 million years ago. But don't worry too much. The chances of one hitting us are tiny. Most GRBs happen in galaxies far, far away. In fact, the furthest GRB ever recorded came from a galaxy more than 13 billion light-years from Earth. That means it happened when the universe was still very young, just a few 100 million years old. The speed of these bursts is also very interesting. Most long-duration GRBs last between 20 and 30 seconds. That's it. They give off more energy in that short time than all the stars in the universe put together. If you light a match, it will flash brighter than 1 trillion suns. This is why experts are rushing to learn more about them. They can tell us about how black holes form, how matter reacts to being under a lot of pressure, and even about what the world was like in the beginning. We use special space telescopes like NASA's Swift and Fermi satellites to catch these bursts when they happen. Because they're so fast, we need telescopes that can turn quickly and start recording almost instantly. Once a burst is spotted, telescopes around the world rush to take a closer look before it fades. And fade it does. After that brief flash of gamma rays, the GRB leaves an afterglow in X-rays, visible light, and radio waves, which can last for days or weeks. That afterglow helps scientists find the host galaxy and learn more about what caused the burst. Some gamma-ray bursts have been so bright, they were visible to the human eye. In 2008, one burst was seen from Earth with just the naked eye, even though it came from a galaxy 7.5 billion light-years away. That's halfway across the observable universe. Think about that. Light from an explosion halfway across the cosmos was bright enough to see without a telescope. That's how powerful these things are. There are still many questions. Why do some stars explode into GRBs and others don't? Could some GRBs actually be signs of exotic physics we haven't discovered yet? Some scientists have even suggested they could be used to test theories of space-time itself. because the gamma rays may interact with the very fabric of the universe as they travel. Stellar collisions, when two suns collide. There are times when space is not as cold, quiet, or still as we think it is. Stars do collide every once in a while, not just slide past or pull apart because of gravity, but really hit each other. When this happens, huge explosions, new kinds of stars, waves of radiation, and sometimes even the birth of black holes are the effects. These are crashes between stars, which are very rare, very powerful, and some of the most energetic events in the universe. How can stars with so much space between them ever collide? After all, our own Sun sits about 150 million kilometers from Earth, and the next closest star is over 40 trillion kilometers away. But in the dense centers of star clusters or in the chaotic aftermath of a galaxy merger, stars can get crowded. Packed tightly together, their orbits get jumbled, and sometimes two stars pass close enough to pull on each other, or slam together entirely. Neutron stars, which are the very dense cores left over when a massive star bursts in a supernova, are one of the most extreme cases. When two neutron stars go around each other, they slowly spiral in toward each other, losing energy as they do so by giving out gravity waves. It is called a kilonova when they finally hit each other. Not only is it bright, but it also makes metals like gold, platinum, and uranium, and sends them into space to help start new worlds. The 2017 event, known as GW 170817, was the first time humans detected this kind of collision. Gravitational wave detectors on Earth felt the ripple of two neutron stars smashing into each other 130 million light-years away. Moments later, telescopes picked up a bright flare of light and radiation. It was a stunning confirmation, not only of what happens when stars collide, but of how some of the rarest elements in the universe are made. But not all stellar collisions involve neutron stars. Sometimes regular stars, like our Sun, can crash too. When that happens, the two stars can merge into a single, larger star. This new star is often unusually bright and unstable, pulsing or spinning rapidly. These events are called stellar mergers, and they're thought to produce strange stars known as blue stragglers, which look much younger than the rest of their stellar neighborhood. A pair of stars called KIC 9832227 is a well-studied example of a possible upcoming collision. Scientists thought for a while that the two stars were moving toward merging and that they might hit each other in our lifetimes. They even said there would be a beautiful red nova that could be seen with the naked eye. New information changed that schedule, but the excitement showed how rare and big these events really are. Stellar collisions can also create supernovae. In some tight binary systems, one star can steal material from its partner. If that partner is a white dwarf, an Earth-sized remnant of a dead star, it might eventually collect so much matter that it explodes in a type Ia supernova. These are so bright that they can outshine an entire galaxy and are used to measure cosmic distances across the universe. And what if one of the stars in a collision is already a black hole? If a black hole collides with a neutron star or another black hole, the result is a violent burst of gravitational waves and sometimes gamma-ray flashes. These events help scientists test the limits of general relativity and understand how massive objects warp space itself. The aftermath of a stellar collision can vary wildly. It might form a new, massive star, or a collapsed object like a black hole. It might send shock waves through nearby gas clouds, triggering new star formation. It might release jets of high-speed particles, or create a glowing remnant that lasts for thousands of years. In the universe's busier spots, like the hubs of galaxies or globular clusters, it may not be uncommon for stars to crash into each other. This could change how stars change over billions of years, how groups grow, and even how galaxies form and change. But even outside those dense areas, stars can meet in slow-motion catastrophes. It just takes time. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy. When that happens, stars from both galaxies will be flung into new orbits. And while most will miss each other, some will crash. The night sky will be filled with new light, new stars, and possibly new collisions. Magnetars, the most magnetic objects ever detected. The power of a magnetar is so great that it would be impossible to compare it to anything else in the universe. That includes every fridge magnet, every MRI machine, and even the Earth's magnetic field. One type of neutron star is a magnetar. A neutron star is the crushed core that is left behind when a huge star bursts. It's not just any neutron star, though. The magnetic field of a magnetar is so strong that it could wipe out your credit card from a very long way away. When a huge star dies in a supernova, the core collapses. If the collapse happens under just the right conditions, fast enough, with just the right spin and mass, it forms a neutron star with a twisted, supercharged magnetic field. This new star, only about 20 kilometers across, spins incredibly fast and holds a magnetic field up to 1,000 trillion times stronger than Earth's. That's 1 followed by 15 zeros. To get an idea of how strong that is, think about this. A magnetar's magnetic field could break your atoms apart if you were only 1,000 kilometers away. Not just beat you up, but pull your electrons away from your center. Not only does it bend space, but it also messes with the building blocks of matter. Magnetars don't stay calm for long. They are known for violent outbursts of energy, sometimes called starquakes. Just like the Earth's crust can crack and shift in an earthquake, the crust of a magnetar, made of super-dense material, can snap under the strain of its own magnetic field. When this happens, it releases a burst of X-rays or gamma rays that can be detected across space. Some of these flares are so powerful that they've affected satellites and communication systems here on Earth. In 2004, one such flare came from a magnetar called SGR 1806-20, located 50,000 light-years away. That explosion was so strong, it briefly compressed Earth's magnetic field. The burst carried more energy than the Sun emits in 150,000 years, and it came from a star the size of a city. Magnetars also spin incredibly fast. When they are first born, they can complete a rotation in less than a second. Over time, that spin slows down, but their magnetic field remains intense for thousands of years. Because they spin and have such strong magnetic fields, they can also shoot out beams of radiation. If those beams sweep past Earth, we can detect them like a lighthouse. These are known as soft gamma repeaters and anomalous X-ray pulsars, both believed to be types of magnetars. Magnetars are very unique because their magnetic fields are so strong that they change the way science works around them. When you get close to the top, empty space itself starts to feel strange. This magnetism is so strong that it can cause something called vacuum birefringence. This is when light bends in a way that shouldn't be possible in normal situations. Scientists who use antennas to measure polarized light from magnetars have seen hints of this. This could be proof that magnetars change the very structure of space. Out of the thousands of neutron stars we've found, only a few dozen show the signs of being a magnetar. That makes every new discovery a big deal. Finding one can help scientists understand how stars die, how matter behaves under pressure no lab on Earth can replicate, and even how elements like gold and platinum might be formed. Magnetars might also be connected to other mysteries. Some scientists believe that certain fast radio bursts, those sudden, intense flashes of radio waves from distant space, might come from magnetars. In fact, one fast radio burst was traced back to a magnetar in our own galaxy in 2020, the first time we've ever connected a burst to a specific source. That gave us a huge clue about what might be causing these strange signals from space. It's possible that these stars also help black holes form. A magnetar could turn into a black hole if it gets too much mass, which could happen if it eats matter from a partner star. That means magnetars are not only very strong, but they may also not last long. They are like cosmic time bombs that can go off at any moment. Hypernovae, the explosions that birth black holes. Stars don't all die in silence when they die. Some come to an end with a supernova. A hypernova, on the other hand, is an even stronger form of this kind of death. If a normal explosion is like a cosmic gunshot, then a hypernova is like a bomb going off. It's one of the worst things that can happen to a star in the world. It doesn't just leave bright gas behind at the end, it creates a black hole. Hypernovae come from the deaths of extremely massive stars, often 30 times or more the mass of our Sun. These stars burn through their fuel fast. While our Sun has a lifetime of about 10 billion years, these giants live only a few million years before they start to collapse. Once they run out of nuclear fuel in their core, no more hydrogen, helium, or heavier elements to burn, they can no longer hold themselves up against gravity. That's when things go south. In a regular supernova, the core collapses into a neutron star, a super dense ball of matter. But in a hypernova, the collapse goes even further. The core's mass is so great that even the pressure from neutron matter isn't enough. It crushes itself into a black hole. This is where things really get complicated. As the core of the star falls in, the surrounding layers blow up and spread out. But this blast isn't going in all directions like most supernovae do. It often instead forms jets, which are thin beams of matter and energy that shoot out at almost the speed of light. These jets have more energy than 100 supernovae put together and can blast through the star's outer shell and into space. These jets are so powerful that they can create a gamma-ray burst, the brightest, most energetic explosion in the known universe. In fact, many long-duration gamma-ray bursts are believed to be the result of hypernovae. That means in just a few seconds, the dying star outshines the entire visible universe, lighting up the cosmos with energy we can still detect billions of light-years away. In 1998, SN 1998 BW happened, which is one of the most well-known hypernova events ever seen. This explosion happened in a galaxy about 140 million light-years away from Earth. It was linked to a strong gamma-ray burst. Scientists were able to connect these dangerous space flashes to hypernova thanks to it. GRB 130427A was another example. It was so bright and powerful that the afterglow could be seen by even small telescopes on Earth. In the moments after the explosion, new elements are forged. The intense heat and pressure during the blast create heavy elements like gold, platinum, and uranium. These elements are then blasted into space, where they become part of future stars, planets, and maybe even life. Every piece of gold on Earth was likely born in an explosion like this. What causes some stars to die in hypernova, while others simply go supernova? A lot of it has to do with rotation and metallicity, the amount of heavy elements inside the star. If a massive star is spinning rapidly and has low metallicity, like those in the early universe, it's more likely to form the jets needed for a hypernova. That's why scientists believe hypernovae were more common when the universe was young and stars were purer and faster. In a different and interesting twist, hypernovae may help shape galaxies. It doesn't just light up space when one bursts, it pushes. Shockwaves from a hypernova can push down on gas clouds nearby, which can lead to the birth of new stars. Or they can blast all the gas out of a galaxy, which stops stars from forming. This kind of event changes the lives of galaxies on a huge scale. Despite their power, hypernovae are rare. Only a small number of massive stars explode this way. But when they do, they leave a legacy that echoes across space and time. They mark the birth of a black hole, the creation of the universe's heaviest elements, and sometimes the brightest flash ever seen. Quasars, supermassive black holes lighting up the cosmos. Some things in space are so bright that they shine like a trillion suns. We can see them from billions of light-years away because they are so bright. Their light began moving toward us before Earth even existed. There is a monster called a supermassive black hole at the center of each of these bright objects, which are called quasars. But wait, black holes don't shine, do they? How can something that gets its power from a black hole be the greatest thing in the universe? This is how it works. one that is millions or billions of times the mass of the Sun starts pulling in huge amounts of gas and dust from its galaxy. This is called a quasar. Things like this don't just fall into the black hole. Instead, it circles around it in a ring, making it very hot because of the friction and gravity. That disk gets so hot that it shines brighter than the whole galaxy put together. That's what we call a quasar. Some quasars are so far away that their light takes over 13 billion years to reach us. That means we're seeing them as they looked when the universe was just a few 100 million years old. They are cosmic time machines, giving us a glimpse of what galaxies were like in the very beginning. The size of quasars is one of the oddest things about them. The part of a quasar that shines might be as small as our solar system, but it is brighter than all the other stars in a galaxy with billions of them. That's like having a flashlight in your hand that shines better than a city at night. The energy involved is hard to imagine. A single quasar can put out more energy in a second than the Sun will emit in 10 billion years. And they keep this up for millions of years at a time. They are engines of pure fury, cosmic furnaces that feed on everything around them. When astronomers first discovered quasars in the 1960s, they were confused. These things looked like stars through a telescope, but their light didn't match anything we knew. Only later did scientists realize they were seeing the brilliant centers of distant galaxies, powered by black holes so massive and active they lit up the universe. Quasars also create powerful winds and jets. As matter falls into the black hole, some of it is blasted out at nearly the speed of light. These jets can shoot out for thousands of light years, pushing gas out of the galaxy and stopping new stars from forming. In a strange way, quasars are both creators and destroyers. They light up the cosmos, but also shut down galaxies by blowing away the stuff needed to make stars. Ton 618 is the name of one of the strongest quasars ever found. One of the biggest black holes we know of is there. It has 66 billion times the mass of the Sun. It's been more than 10 billion years since this monster's light left Earth. Even from Earth, Ton 618 would be too bright to see if it were in the middle of our galaxy. But not all quasars are easy to spot. Some are hidden behind clouds of gas and dust. These obscured quasars still shine like crazy, but we have to use infrared and X-ray telescopes to see them. As technology improves, we're finding more and more of these hidden giants, and it turns out they might be more common than we thought. Quasars also help scientists study dark matter and dark energy. Since they're so bright and far away, their light passes through massive regions of space before reaching us. That light can bend and twist due to gravity, a phenomenon called gravitational lensing. When a quasar's light is bent by something massive, like a galaxy cluster, we can use that bending to learn about the invisible matter in between. Even though quasars are very strong, they don't last forever. In the end, the black hole eats everything close, and the quasar stops working. After that, the galaxy goes quiet, and the black hole can't be seen again. But if a new source of gas comes in, some galaxies might wake up again, like a zombie quasar coming back from the dead. The most luminous stars, Wolf-Rayet and hypergiants. Some stars don't just shine, they roar through space like firestorms in the sky. Wolf-Rayet stars and hypergiants, which are huge fires that shine light millions of times brighter than our Sun, are some of the most powerful and short-lived things in the universe. Big changes happen in the galaxies around these stars because they burn quickly and die young. Scientists still don't fully understand how they form, change, and fall apart because they are so extreme. Wolf-Rayet stars, often written as WR stars. These are not ordinary stars. They are the stripped-down, exposed cores of once massive stars that have shed their outer hydrogen layers. What's left behind is a core so hot and unstable that it blasts out fierce stellar winds, moving at over 2,000 kilometers per second. These winds are powerful enough to blow away the star's own mass over time. WR stars are different because they show their guts. They don't just give off gas like other stars do. Instead, their light shows helium, nitrogen, carbon, or oxygen, based on how far along they are in the process of nucleosynthesis. A lot of what we're seeing are nuclear ashes, which are proof of fusion events that happen deep inside the stars. The brightness of their glow is so strong that it would melt our solar system in seconds. Wolf-Rayet stars are also ticking time bombs. Because they're so massive and burn fuel so quickly, they don't last long, just a few 100,000 years at most. That's nothing compared to stars like our Sun, which will shine for billions of years. And when a WR star reaches the end of its life, it often explodes in a violent hypernova or becomes a gamma-ray burst, sending deadly radiation across space. But even WR stars pale next to hypergiants. A hypergiant is the cosmic equivalent of a heavyweight boxer on fire. These stars are among the largest and brightest in the universe. One of the most famous, VY Canis Majoris, is over 1,000 times the Sun's diameter. If it replaced the Sun in our solar system, it would engulf Mercury, Venus, Earth, Mars, and possibly even Jupiter, and its brightness? Roughly 300,000 to 500,000 times that of the Sun. Another mind-blowing example is Eta Carinae, a star system so unstable that it once erupted in the 1800s in an explosion almost as bright as a supernova, but it survived. That blast released more mass than our entire Sun in just a few decades, and today it's still surrounded by a glowing shell of gas called the Homunculus Nebula, a reminder of that stellar tantrum. Eta Carinae is expected to end its life in a colossal supernova or hypernova, possibly creating a black hole and unleashing a jet of energy that could affect life on Earth if we were closer. It is very dangerous to approach hypergiants and WR stars because they are hard to predict. Their upper layers are always moving, sending mass in all directions. They flash, pulse, and lose their own atmosphere in huge storms. In 1 year, some lose more than 1 million times Earth's mass. That's the same as throwing a planet into space every 2 weeks. These extreme stars are more than just cosmic fireworks. They play a key role in recycling the universe. Their violent deaths scatter heavy elements like carbon, oxygen, and iron, ingredients for planets, oceans, and life. Without them, the universe would be a much simpler and duller place. Interestingly, most of these stars are found in stellar nurseries, like the Tarantula Nebula in the Large Magellanic Cloud. That's where the famous WR star R136A1 lives, believed to be one of the most massive stars ever discovered, with more than 200 times the mass of the Sun. This star alone emits 8.7 million times more light than our Sun. It's so intense that it's already shedding mass through constant radiation, and it will likely explode in the near future. But studying them isn't easy. Many hypergiants and WR stars are shrouded in dust, hidden behind their own debris. Astronomers rely on space telescopes like Hubble, Spitzer, and the James Webb Space Telescope to peer through the haze and capture their details in infrared light. Every observation adds a new piece to the puzzle of how stars live, die, and give birth to the next generation. Neutron stars, the densest matter in the observable universe. Take something Manhattan-sized. Now pack all of the Sun's mass into it. You get a neutron star, which is one of the coolest, strangest, and strongest things in the world. They are what's left over when a very large star explodes in a supernova. They go against everything we think we know about matter, gravity, and even time. When a massive star runs out of fuel, its core collapses under its own weight. The outer layers explode outward in a supernova, but the core doesn't disappear. It gets squeezed, hard. So hard that protons and electrons inside atoms get crushed together into neutrons. What's left is a ball made almost entirely of neutrons. It's like a giant atomic nucleus, but 20 kilometers wide and heavier than 1.4 times the mass of the Sun. Just to give you an idea, a teaspoon of neutron star matter would weigh more than 1 billion tons. That's about the same size as Mount Everest. Take that in. If it didn't fall through the Earth, melt through the core, and kill everything in its way, you could hold a piece of a neutron star in your hand. But neutron stars are not just dense. They're also fast. When they're born, they spin incredibly rapidly, sometimes hundreds of times per second. These spinning neutron stars are called pulsars, and they send out beams of radiation from their magnetic poles. Every time the beam sweeps past Earth, we see a pulse of light, like a cosmic lighthouse. Some pulsars spin so steadily that they keep time better than atomic clocks. Their magnetic fields are also intense, millions or even trillions of times stronger than Earth's. In some cases, the magnetic field is so extreme that it qualifies the star as a magnetar, which we've already covered. This magnetism can twist and stress the surface of the star until it cracks, releasing giant bursts of energy called starquakes. Inside a neutron star, the physics gets even weirder. The pressure is so high that we don't know exactly what's going on in the core. Some theories suggest that the neutrons themselves break down into a soup of quarks, the even smaller particles that make up neutrons and protons. If that's true, then the center of a neutron star might be the densest state of matter anywhere in the universe, a place where physics as we know it stops working. These stars are fragile in a strange way. If a neutron star gains too much mass from eating up matter from a nearby companion, or from merging with another neutron star, it collapses further into a black hole. That's how fine the line is between two of the universe's most extreme objects. Neutron stars are also key to one of the most important discoveries in modern science, the production of heavy elements. In 2017, scientists detected gravitational waves from two neutron stars spiraling into each other and merging. The event, called GW170817, also released light across the electromagnetic spectrum. From X-rays to radio waves, telescopes watched the aftermath in real time. And what they saw was groundbreaking. The collision produced gold, platinum, and other heavy elements. That means some of the jewelry we wear, and even some of the atoms in our bodies, were forged in the crash of two dead stars. Also, these stars don't just stand there. Some people move through the galaxy very quickly. Neutron stars are made by explosions that are so powerful that they can hit other objects very hard. As they race through the Milky Way, some are going hundreds of kilometers per second, in a disk the size of a city. There are also different kinds of neutron stars. Some are millisecond pulsars, which mean they spin hundreds of times every second. Some are X-ray binaries, which brighten up in X-rays by eating matter from a close star. Some of them are even glitching pulsars, which means they change the speed of their spin all of a sudden. Scientists are still trying to figure this out. Neutron stars have big effects on the world, even though they are very small. Physics, nuclear physics, and even space-time itself can't be studied without them. In these tests, they see how far matter can go. They are tougher than our best models. They also sometimes show us things we didn't expect. Blazars, quasars with jets aimed straight at us. As an example, picture a fire hose sending out so much energy that it could destroy a whole world. Point that fire hose straight at Earth now. That's a blazar. It is a unique type of quasar, already one of the brightest and most energetic things in the universe. But there is one big difference. Its jet of energy is pointing almost straight at us. Because of that small change, blazars look even more fierce, dangerous and strange than most other things we've found in space. At the center of every blazar is a supermassive black hole, just like in quasars. These black holes are millions to billions of times more massive than our Sun, and they sit at the heart of galaxies, pulling in huge amounts of gas and dust. As this material spirals into the black hole, it heats up and creates jets of particles and energy that shoot out from the poles at nearly the speed of light. Normally, these jets shoot out sideways, and we can see them glowing in radio or X-ray light. But if one of those jets happens to be aimed straight at Earth, we don't just see it, we get blasted by it. That's when a quasar becomes a blazar. The energy in these jets is so focused, so direct, that they become among the brightest things in the sky. even from billions of light years away. One reason blazars are so fascinating is because of a trick called relativistic beaming. This means that the jet looks even brighter and more powerful than it actually is, simply because it's coming toward us so fast. The particles in the jet are moving close to the speed of light, and that makes the light they emit pile up in our direction, like a flashlight being waved directly at your eyes. It's not just bright, it's blinding. But a blazar isn't always screaming at full volume. Sometimes it's quiet. Then, out of nowhere, it erupts with a huge flare, shooting out bursts of gamma rays, X-rays, or visible light. These outbursts can happen in hours, minutes, or even seconds. Some have changed brightness by more than a factor of 10 in less than a day. That's a level of variability that makes them really hard to predict, and really exciting to study. Blazars are also known for something scientists call polarization. This means that the light waves coming from the jet are all lined up in a specific way. It tells us that the jet is filled with magnetic fields, guiding the charged particles along like rails in a roller coaster. By studying that polarization, astronomers can learn about the structure of the jet, the speed of the particles, and even how close the jet comes to the black hole. Lacertae is one of the most well-known blazars. It is so bright that optical telescopes can see it even though it is hundreds of millions of light years away. Another is 3C279, which has been seen to explode in gamma rays with energies that can't be explained. A blazar named TXS 0506 plus 056 was the first source of a high-energy neutrino to be found on Earth in 2018. A neutrino is a ghost-like particle that can go through anything, even worlds, without getting stuck. Because of that find, blazars are now linked to some of the strangest and strongest particles in the world. These blazars might be cosmic particle generators, which is even bizarre. Think about the Large Hadron Collider, which is the world's largest machine for smashing particles. Atoms can move almost as fast as light with its help. But blazars naturally do that on a much larger scale by sending out cosmic rays with very high energies that go all the way across the universe. Some of these particles hit the Earth's atmosphere every day, and some may come from blazars. Even though blazars are incredibly far away, usually billions of light years, they have real effects here on Earth. Their gamma rays can be detected by space telescopes like NASA's Fermi Gamma Ray Space Telescope or ground-based detectors like the Cherenkov Telescope Array. By watching their flares and jets, we're learning how black holes grow, how galaxies evolve, and how energy moves through space on the grandest scales. Planck energy, the highest theoretical energy a particle can have. This is the most powerful thing in the world that can get. It's called the Planck energy. In normal life, you probably haven't heard of it because nothing else on Earth comes close. But there is a secret limit in the rules of physics. There is no more energy that a single particle can hold before the world itself says, enough. What does Planck energy really mean? It's the amount of energy you'd get if you kept trying to pack as much energy as you could into a single object, like an electron or a proton. In the end, if you did it for too long, you wouldn't just get a particle that was supercharged, you'd tear space-time apart. It would be so full of energy that it would turn into a very small black hole. That's the worst thing about it. To make sense of this number, scientists had to combine the three main forces of nature: gravity, quantum mechanics, and relativity. Planck energy comes from combining three constants of nature: the speed of light, Planck's constant, which governs quantum behavior, and Newton's gravitational constant, which controls gravity. When you mash those together, you get the Planck scale. The Planck energy is about 10 to the 19th giga-electron volts. That's a 1 followed by 19 zeros. Roughly 10 million trillion times the energy of the protons in the Large Hadron Collider, LHC, which is already the most powerful particle accelerator ever built. To reach Planck energy, you'd need a collider the size of the Milky Way galaxy. That's not a joke. That's the actual size required just to get close. But why does this energy matter? Because it marks the point where our current understanding of physics starts to break down. At energies this high, gravity becomes as strong as the other forces. Quantum effects and space-time itself become inseparable. The very idea of distance and time might not work the way we expect. In fact, if a particle ever did reach this energy, it wouldn't act like a normal particle anymore. It would behave more like a black hole. This is why scientists believe the Planck energy is the doorway to a theory of everything, a single framework that combines general relativity, which explains big things like planets and black holes, and quantum mechanics, which explains tiny things like atoms and particles. Right now, those two theories don't work well together, but at the Planck scale, they crash into each other and force us to find a deeper explanation. Some ideas say that we could finally understand quantum gravity, the theory of how gravity works at the smallest levels, if we could study what happens at the Planck energy. Some people think this is where space-time might stop being smooth and start being grainy, like images in a picture. Space might not have to be a smooth surface. It could be made up of small pieces. We don't have the right tools yet to see that, though. Even though we can't create Planck energy particles in the lab, the universe might be doing it naturally. Some ultra-high energy cosmic rays, particles that crash into Earth's atmosphere, come close to these energies. Scientists don't fully understand where they come from. Could it be exploding stars, blazars, or something even weirder? These ghostly bullets from space are like cosmic messengers, hinting at physics we haven't unlocked yet. There's even an idea called the Planck wall, a kind of limit to what we can ever observe. If a particle or event involves Planck-scale energies, it might be hidden from us forever, because it would instantly collapse into a black hole. That means some parts of reality could be fundamentally unknowable, not because we're not smart enough, but because the universe just doesn't let us see beyond that line. And then there's the role Planck energy plays in the early universe. Just after the Big Bang, everything was packed into a tiny space with temperatures and energies near the Planck scale. For the first tiny fraction of a second, the universe may have operated under rules we can't even imagine, rules that no longer apply today. Unlocking the secrets of that time could explain why the universe expanded the way it did, why it formed stars, and even why time flows in one direction. Ultra-high energy cosmic rays, ghost bullets from deep space. Every second of every day, tiny particles that you can't see fall from space all around you. Most of them are safe to touch. They go through you, your home, and the Earth itself without leaving any marks. One of them does, very rarely, crash into the atmosphere with the force of a fast-thrown baseball. It's not even baseball. There is only one atomic particle. These are called ultra-high energy cosmic rays, and they are some of the most mysterious and powerful things in the universe. Cosmic rays are basically particles, mostly protons or atomic nuclei, that zip through space at nearly the speed of light. Most cosmic rays come from the sun or from supernova explosions, but ultra-high energy cosmic rays are in a league of their own. These are particles that carry mind-boggling amounts of energy. One of them can carry as much punch as a speeding truck, yet it's smaller than an atom. Just how powerful are we talking? The highest energy cosmic ray ever detected is nicknamed the Oh My God particle. It hit Earth in 1991. This single particle carried the energy of a well-thrown baseball, not a cloud of particles, not a meteor, just one lone proton. It was moving so close to the speed of light that if a beam of light had been chasing it, it would have taken over 200,000 years to gain even a 1-second lead. That kind of energy is millions of times greater than what the Large Hadron Collider can produce, and we still don't know what created it. Ultra-high energy cosmic rays hit Earth only a few times per square kilometer each century. That means you could go your entire life and never have one hit your head, but scientists are on the lookout. Huge observatories like the Pierre Auger Observatory in Argentina use hundreds of detectors spread across vast landscapes to catch them. When a cosmic ray hits the atmosphere, it creates a shower of secondary particles that spread out over kilometers. By measuring those showers, scientists can figure out how much energy the original particle had, and maybe even where it came from. We still don't really know where these ghost bullets are being fired from. They might come from supermassive black holes, colliding galaxies, or massive jets from blazars. They might even come from things we haven't discovered yet, exotic objects or events beyond our current understanding. Some theories suggest they're the leftovers of ancient cosmic strings, hypothetical threads of energy left over from the Big Bang. And because these particles are charged, their paths get bent by magnetic fields as they travel through space. By the time they get to Earth, they've zigzagged so much that we can't trace them back to their original source. It's like trying to figure out where a bullet came from after it's bounced off 1,000 walls. The universe should have a speed limit for these particles, called the GZK cutoff. This idea, named after 3 scientists, says that particles above a certain energy should lose power as they travel through space because they crash into photons from the cosmic microwave background, the leftover light from the Big Bang. It's like trying to run through a fog of invisible energy. But some particles seem to break that limit. They arrive at Earth with more energy than they're supposed to have. Either we're misunderstanding the rules, or there's something new going on out there. That's what makes these cosmic rays intriguing. They could be the keys to universes that are hidden. They might be coming to us from things we can't see. They could also be proof that our ideas about space, time, and energy are very wrong. Some scientists think we might eventually use cosmic rays to study dark matter, test quantum gravity, or explore the structure of space itself. If we can figure out what's shooting them and why, we'll be opening a whole new window into the universe. But they're amazing even without that. Just picture a proton, a very small particle of matter, moving through space by itself for millions or billions of years. It's possible that it began its trip before Earth was made. It went by gas clouds, galaxies, and stars. It finally hit our atmosphere one day, with a bang that was big enough for us to hear. The Great Attractor, a gravitational pull beyond galaxies. As the universe grows, galaxies are moving farther apart, like the dots on a balloon that is rising. But not all of them. Not all galaxies are just floating out there. They are being pulled, not easy, in the direction of something we can't see, something very big, something strange. Astronomers call that something the Great Attractor. In the 1980s, scientists were measuring the speed and direction of nearby galaxies to understand the large-scale motion of the universe. They expected galaxies to be moving away from each other evenly in all directions due to the Big Bang. But that's not what they found. Instead, they noticed that our own galaxy, the Milky Way, along with thousands of others, was moving toward a specific region of space. It wasn't just a small drift. We're traveling at about 600 kilometers per second in that direction. That's over 2 million kilometers per hour. What is it that's pulling us? That's the main question. The area we're moving toward is called the Great Attractor, and it's in a sky area that is blocked by the Milky Way's thick center. It is hard for light to get through this area because it is full of stars, gas, and dust. It is known as the zone of avoidance by astronomers. Not that we're ignoring it, but it's really tough to see through it. Using X-ray and infrared telescopes, which can peek through the dust, scientists have started mapping what's back there. And what they found was mind-blowing. There's an enormous concentration of galaxies behind the curtain. One of the biggest is a galaxy cluster called Norma Cluster. It's a monster filled with thousands of galaxies, and it's part of a larger structure that spans hundreds of millions of light years. Even that doesn't fully explain the pull. The Great Attractor seems to be part of an even bigger structure called the Laniakea Supercluster, a name that means immeasurable heaven in Hawaiian. This supercluster includes our Milky Way, the Virgo cluster, and about 100,000 other galaxies, and all of them are being drawn toward a dense region near the Great Attractor. The galaxies don't just stop at the Great Attractor. Observations show that many continue beyond it, toward an even more distant, more massive region called the Shapley Supercluster. It's like the Great Attractor is just a stepping stone, an exit ramp on a massive cosmic freeway, and the real destination is even farther away. But we're not sure. Because the truth is, we still don't know exactly what's there. It's not just a place. It's a gravitational mystery. An invisible force moving entire clusters of galaxies like leaves in a river. It challenges our understanding of how matter is spread across the universe. It suggests that the cosmos isn't smooth and even. It has currents, flows, hidden depths. Some researchers have even speculated that dark matter might be playing a role. Maybe the Great Attractor is filled with invisible matter, stuff we can't see, but which adds enormous mass. Or maybe the shape of space-time itself is bending in ways we don't yet understand, creating a gravitational well we can't fully measure. There's no sign that the Great Attractor is dangerous to us. It's not like we're going to crash into anything. Space is so vast that even when galaxies move toward one another, collisions take billions of years, and often pass right through due to the empty space between stars. But it really does have an effect. It has an effect on our galaxy, our local group, and large parts of the universe. It shows that the universe has order on a level that is hard to imagine. We used to think that gravity only went so far. Huge, unknown things can pull at the very foundations of space. We're still trying to map it, still trying to measure it. And as we improve our telescopes and surveys, we're beginning to lift the veil. Piece by piece, the picture becomes clearer. But even now, decades after it was first discovered, the Great Attractor remains a cosmic enigma, a reminder that some of the most powerful forces in the universe don't come with bright lights or dramatic explosions. Cluster collisions, cosmic smash-ups that reshape space. There's more to galaxies than just floating around in space. Galaxy clusters are huge groups of galaxies that move together. Each cluster can hold hundreds or even thousands of galaxies, as well as huge clouds of hot gas and strange dark matter. Now, picture two of these huge groups colliding with each other. Not just a few stars bumping into each other, but whole galaxy cities crashing into each other in slow-motion wrecks that last for billions of years. These are galaxy cluster collisions, some of the most powerful and energetic events in the universe since the Big Bang. Let's be clear, when we say collision, we don't mean like cars hitting on a highway. Space is big. Even in these massive events, individual stars almost never hit each other. Instead, the galaxies within each cluster pass through each other like ghosts. But it's the other stuff, especially the clouds of hot gas, that feel the full impact. Between the galaxies in a cluster is something called intracluster gas, hot plasma that can reach temperatures of tens of millions of degrees. When two galaxy clusters slam together, their gas clouds don't pass through. They crash, hard. The shock waves heat the gas even more, causing it to glow brightly in X-rays. These glowing clouds can be so large that we see them clearly with space telescopes like Chandra and XMMM Newton. The bullet cluster is one of the best-known examples of this. The name comes from the way it looks, like a bullet went through a cloud of gas. A smaller cluster went through a bigger one, and the hot gas between them crashed into each other. But here's the catch. Experts found something strange when they figured out where the cluster's mass really was. The gas wasn't where most of the mass was. It went right through, just like the galaxies. That mass you can't see, that's dark stuff. Dark matter is real, and the bullet cluster is one of the best proofs of that. It proved that the stuff that glows and gets hot isn't what makes up most of the universe's mass. Normal matter doesn't react with it in the usual way. It can't be seen, but it has weight. We can see dark matter move ahead of the rubble when two groups crash into each other. A typical galaxy cluster is about 10 million light-years across. When two of them merge, they don't just cause a bright flash and stop. These are events that unfold over billions of years. First, the clusters pass through each other. Then they swing around. Gravity pulls them back together. They crash again. Over time, they settle into a new, larger cluster. And with each collision, the universe changes. Cluster collisions release unimaginable amounts of energy. In fact, they are the most energetic events since the Big Bang itself. The heat and shock waves ripple across space, stirring up the gas and triggering bursts of star formation in some galaxies while stripping others bare. The chaos can switch galaxies off, stopping them from making stars by removing their gas. Or it can slam them with enough force to light up new stars in a cosmic blaze. These collisions also stretch space itself. When massive objects accelerate or crash together, they send ripples through the fabric of space-time, gravitational waves. Most of the ones we've detected so far come from black holes and neutron stars. But in theory, massive galaxy cluster collisions should also produce gravitational waves, though much weaker and at much lower frequencies. With future detectors, we might be able to catch those whispers from cosmic car crashes. And then there's radio relics, giant arcs of radio emission found at the edges of colliding clusters. They form when shock waves from the collision accelerate electrons to nearly light speed. These electrons spiral around magnetic fields and give off radio waves. The result is enormous, glowing structures that mark where the shock front is moving through the gas. No matter what kind of galaxy it is, every cluster impact has a story to tell about the universe as a whole. By looking at how the galaxies react to changes in dark matter, how the hot gas moves, and how the dark matter shifts, we can learn about gravity, how the universe evolved, and even the mysterious dark energy that makes it expand. Black hole mergers, ripples of mass colliding in space-time. For millions of years, imagine two giants that you can't see, each made of pure gravity, dancing in a silent circle. As they spin faster and faster, they get closer and closer until they finally crash. When they do, they don't just shake the area around them. They make the very fabric of space shake. We've seen a black hole merge. It's also one of the most powerful and mind-bending things that the universe can do. Black holes are already peculiar. There are places in space where gravity is so strong that nothing can get away, not even light. Things can get weirder though. If two black holes grow close to each other, like when two big stars in a pair system die, they might slowly move toward each other. As they move, they lose energy by putting out gravitational waves, which are ripples in space-time that you can't see. For years, these waves were just a prediction. Albert Einstein's theory of general relativity said they should exist, but no one had ever seen one. That changed in 2015. The LIGO Observatory, two giant detectors located in the US, picked up a tiny wobble in space itself. The signal lasted just a fraction of a second, but it was unmistakable. Two black holes had merged about 1.3 billion light-years away. This wasn't just a cool discovery, it was historic. It was the first time humanity had ever detected a cosmic event using something other than light. We didn't see the crash, we felt it, and it opened up a whole new way to observe the universe. In that one black hole merger, about 3 times the mass of the Sun was turned into pure energy, in the form of gravitational waves. That means, for a split second, the event released more energy than all the stars in the observable universe combined. Think about that. The entire night sky, all the stars we've ever seen, couldn't match the raw force of those two merging black holes. And the only thing left behind was a slightly bigger black hole. Since then, scientists have detected dozens more mergers. Some involve black holes that are about the same size, 10 or 20 times the mass of the Sun. Others involve truly gigantic ones, with 50, 80, or even over 100 solar masses. In 2020, LIGO and its partner Virgo detected a merger that created a black hole weighing about 142 times the mass of the Sun, the first clear evidence of a class called intermediate mass black holes. We'd never seen one before. Every time we detect a new merger, we learn something new. How do black holes form? Do they always come from stars, or can they grow from other black holes eating each other? Can black holes get kicked out of galaxies after merging? What happens in the exact moment of collision when gravity is at its most extreme? These mergers also help us test the limits of physics. Gravitational waves don't just tell us that something happened, they tell us how space itself responds to massive motion. If there were any cracks in Einstein's theory, black hole mergers would expose them. So far, relativity is holding up. But one day, we might catch a signal that doesn't fit, and that could change everything. The technology behind detecting these mergers is almost as amazing as the events themselves. LIGO works by bouncing lasers between mirrors set kilometers apart. If a gravitational wave passes through, it stretches one arm of the detector slightly by less than the width of a proton. And yet, we can measure it. It's like detecting a ripple in a pond from a continent away. Soon, new detectors like LISA, Laser Interferometer Space Antenna, will go into space. This will allow us to catch even bigger, slower black hole mergers, like those involving supermassive black holes in the centers of galaxies. These will send out longer, deeper gravitational waves that ground-based detectors can't hear. It's like switching from a flute to a bass drum. When we talk about supermassive black holes, they also join, but it takes a lot longer. When galaxies crash into each other, their center black holes may finally spiral into each other and join. It could take millions or billions of years for this process to finish, but when it does, the final merger will be huge, sending huge waves of gravity across the universe. We're sure they'll come, but we haven't caught one yet. What takes place after a merger? The new black hole can sometimes get a boost from the uneven release of energy and fly through space. If it was close to the galaxy's center, it might even be able to get away. That means there may be black holes flying through the universe that can't be seen and can't be stopped. They were made by past crashes. White holes, theoretical time-reversed black holes. Things like light, matter, and even time are known to be pulled into black holes. Things are gone for good once they cross the event horizon. But what if the reverse was true? A kind of cosmic stream that sends matter and light out into space instead of taking them in. That's what a white hole is all about. A black hole that flips time and does the exact opposite of what we think gravity would do is one of the strangest and most extreme possible things in physics. In simple terms, a white hole is a region of space that nothing can enter, but things can leave. It's like a black hole running in reverse. Instead of pulling matter in and never letting it escape, a white hole constantly pushes matter and energy out and doesn't allow anything to cross its boundary from the outside. If black holes are cosmic drains, white holes are cosmic blowtorches. These objects come directly from the math of general relativity. When scientists solve Einstein's equations to describe a black hole, they sometimes find a mirror solution, one that looks the same but runs backward in time. That's where the concept of a white hole came from. But just because math allows it doesn't mean nature builds it. So far, we've never seen one. No telescope has ever found a spot in space where matter is endlessly exploding out without anything falling in. White holes are still completely theoretical, but that hasn't stopped scientists from asking, what if they're real? There is a big theory that black holes and white holes might be linked by something called a wormhole. Imagine a tube going through space and time. That's what a wormhole is. It's possible for a black hole to be one end of a wormhole and pull things in, while a white hole could be the other end, and spit them out somewhere else in the universe, or even in a different universe. People have been writing science fiction with this idea for a long time, and it also shows up in real physics studies. Some physicists think black holes might become white holes. According to quantum theory, nothing can be lost forever, not even inside a black hole. But black holes seem to trap information in a way that violates that rule. To solve this information paradox, some theories suggest that black holes might eventually die, not by slowly evaporating like Hawking predicted, but by exploding into white holes. In this model, the black hole collapses, then bounces back, releasing all the information it once swallowed. This bounce idea is tied to a theory called loop quantum gravity, which tries to merge quantum mechanics and general relativity. In loop quantum gravity, space itself has a kind of atomic structure. That means when a black hole gets small enough, space can't compress anymore, and the collapse reverses. Instead of forming a singularity, it becomes a white hole. The universe hits rewind. If that's true, then white holes could be real, but just incredibly short-lived. We wouldn't see them because they only flash into existence for a moment, spitting out all the matter the black hole once swallowed, then vanishing. It would be like a cosmic burp after billions of years of silent digestion. Some ideas even say that the Big Bang could have been a white hole himself. Think about it. All matter, energy, and space would be thrown out of a single-point explosion. It fits what was said. Some experts think that our universe might have started out as a white hole, or even as the death ray of a black hole in a different universe. Of course, that hasn't been proven, but it does show how crazy the options are. So why haven't we seen a white hole? For one, they might be extremely rare, or only exist under conditions we can't yet observe. They also might be unstable. If anything tries to fall into a white hole, the math says it should collapse instantly. That makes it hard for them to survive for long, especially in a busy universe filled with stray gas, radiation, and wandering stars. But maybe, just maybe, we've already seen clues. Some fast radio bursts, brief, bright flashes of radio waves from deep space, have unknown origins. A few physicists have wondered if these could be white holes blinking into existence. It's a long shot, but it shows how even the wildest theories are being tested as our instruments improve. Fast radio bursts, 1 millisecond signals from unknown sources. Scientists were looking through old data from an Australian radio station in 2007 when they saw something strange, a short burst of radio energy. It was quick, it was strong, and it came from a very long way away. At first, no one thought it was true. The problem could have been caused by something like a microwave oven or a problem with the tools. It did happen again, though, once more. These mysterious flashes became known as fast radio bursts, or FRBs. Each one lasts less than a blink of an eye, yet carries more energy than the sun emits in a whole day. And we still don't fully understand what's causing them. FRBs are incredibly hard to catch. They arrive without warning, they vanish in milliseconds, and they usually never repeat. You can't point a telescope at one and just wait. It's like trying to catch lightning in space with your eyes closed. That's why, for years, we only had a few examples. But technology got better. Telescopes became faster and smarter. Instruments like CHIME in Canada, ASCAP in Australia, and FAST in China were built to scan the sky constantly, waiting for those telltale blips. Now, we've detected hundreds of FRBs, and some of them have changed everything. Most FRBs are one-time events, a single burst, never seen again. But a few are repeaters. They flash more than once, sometimes on a regular schedule. One repeater, called FRB 121102, has gone off dozens of times from the same spot in the sky. This told scientists that at least some FRBs don't come from exploding stars or dying galaxies. Whatever's causing them survives the event. And the sources, they're spread all over the sky. Some come from galaxies billions of light years away. Others seem much closer. The energy is always huge. One FRB we detected from another galaxy released as much energy in a fraction of a second as our sun emits in 80 years. But we don't see any damage, no exploding star, no black hole merger, just a flash. What could be making them happen? A magnetar, which is a highly magnetic neutron star, is one idea. In 2020, a signal that looked like a FRB was picked up from a known magnetar in our galaxy. This helped prove that magnetars can make at least some FRBs. We caught one in the act for the first time. However, there was one catch: that nearby magnetar had a lot less energy than the ones we've seen in deep space. Either we got lucky and got a small one close by, or the ones farther away are from something much stronger. Other theories include black holes eating stars, neutron stars crashing into things, or cosmic strings snapping in space. There's even speculation that some FRBs could be artificial, signals from advanced alien civilizations. That's not likely, But the fact that scientists are still seriously asking what's behind FRBs shows just how bizarre they are. Another unnatural thing about FRBs is how they get around. The burst goes through clouds of gas, plasma, and magnetic fields as it moves across the universe. In ways that can be measured, this spreads and bends the signal. Scientists can figure out what the FRB went through by looking at that warping. This makes these random space flashes useful for mapping the unseen universe. They also help us find hidden galaxies. Some FRBs come from tiny dwarf galaxies that are hard to spot, but the burst's exact location can lead us to its host, giving us a peek at corners of the cosmos we might otherwise miss. In one case, FRB 180916 was found to repeat every 16 days, like a heartbeat from space. It flashes for a few days, then goes silent, then flashes again. That's incredibly unusual for a cosmic event. It suggests something is orbiting or rotating in a predictable way, maybe a neutron star swinging through a beam of matter or a binary system with just the right conditions. FRBs are also being used to study dark matter. Some scientists think that hidden black holes or other dark matter objects might occasionally bend FRBs through gravitational lensing, creating double flashes or weird distortions. If we see those, it could help us understand what dark matter really is. Even though they're brief, FRBs are incredibly useful. They're like cosmic sonar, pinging through the universe and helping us map what's out there. Every time one goes off, it carries a history of its journey. The big question is still why they happen. There's no way to be sure. They might come from frozen stars, magnetic fields that are bent, crashes between galaxies, or something completely different. They could be rare events or background noise that we're just starting to understand. They might even show hidden facts about gravity, the way space is organized, or the beginning of the world. Supermassive black holes, galactic anchors with relativistic power. We live in the Milky Way, which has a monster at its center called a supermassive black hole. These colossal space rocks are millions or even billions of times heavier than the Sun. Black holes that are enormous are not like stellar black holes, which are made when stars die. They don't just change the things around them, they change whole worlds. They're not just heavy. They are some of the most powerful things in the world and work together to build galaxies. The supermassive black hole at the center of our galaxy, called Sagittarius A star, is about 4 million times the mass of the Sun. But that's small compared to the biggest ones we've found. Some, like the one in galaxy TUN 618, weigh over 60 billion solar masses. That's 60 billion stars worth of mass, compressed into a region smaller than our solar system. And while they're invisible to the eye, we've finally seen one. In 2019, the Event Horizon Telescope gave us the first ever image of a black hole's shadow in galaxy M87, a fuzzy, fiery ring of light surrounding the point of no return. But here's the mind-blowing part. These black holes aren't just cosmic garbage disposals. They don't sit silently in space. They power the brightest objects in the universe, quasars, blazars, and active galactic nuclei. When gas and dust fall into a supermassive black hole, they don't fall in immediately. They swirl around in an accretion disk, heating up due to friction and gravity, until they glow across the electromagnetic spectrum. These disks shine so brightly they can outshine the galaxy that hosts them. Some of this matter doesn't make it into the black hole. Instead, it gets caught up in twisted magnetic fields and launched outward in colossal jets, streams of particles traveling near the speed of light, sometimes stretching for hundreds of thousands of light years. These relativistic jets are so powerful they can punch holes through galaxies, shutting down star formation and spreading energy across intergalactic space. This is where the real power of supermassive black holes becomes clear. They don't just sit at the center of galaxies, they control them. The jets and radiation they produce heat up gas in the galaxy, making it harder for new stars to form. In a sense, the black hole acts like a thermostat, regulating the growth of its host galaxy. Without them, galaxies might grow uncontrollably or collapse under their own mass. There seems to be a mysterious connection between the size of a galaxy and the size of its central black hole. The bigger the galaxy, the bigger the black hole. scientists aren't sure why. Is the black hole causing the galaxy to grow? Or does the galaxy's mass determine the black hole's size? It's one of the biggest puzzles in astrophysics, but one thing is clear. The two grow together. They're locked in a gravitational feedback loop that shapes the structure of the universe. Supermassive black holes also warp time and space in extreme ways. Near the event horizon, time slows down compared to the rest of the universe. Light bends, orbits twist, and physics behaves like it's in a funhouse mirror. These effects aren't just theoretical, they've been measured. Stars orbiting close to Sagittarius A star in our own galaxy speed around at thousands of kilometers per second, their paths bending under the influence of gravity so strong that it matches Einstein's predictions perfectly. But we still don't know how these giants form. Stellar black holes are born when stars die, but supermassive black holes are too big to form that way. Did they grow from smaller black holes over billions of years? Or did they somehow form directly in the early universe from collapsing gas clouds? Some scientists think there may have been seed black holes from the very beginning of time, perhaps even before galaxies existed. These seeds may have grown by gobbling up matter, merging with other black holes, or both. Not all supermassive black holes are active. Many just sit there, dark and quiet, with no swirling disk or blazing jet, but they still have immense gravity and influence. If you dropped a star into one, it would trigger a violent reaction. Possibly a tidal disruption event where the star is stretched and torn into a long stream of gas before disappearing into the void. And what happens when two galaxies join together? In the end, their supermassive black holes will move toward each other and join. Strong gravity waves are sent out by these mergers. These waves are ripples in space-time that we are just now starting to notice. In the future, space telescopes like LISA might be able to record the sound of two giant black holes meeting from the other side of the universe. Relativistic jets, energy beams near the speed of light. Think of something in the universe that is so strong that it can send streams of matter and energy over a very large distance. The speed of these jets is almost as fast as light. They can cut through galaxies and stay focused for millions of years. They don't come from fires or stars. They come from black holes, which are some of the deepest and quietest things in the world. These are relativistic jets, which are some of the most powerful tools that nature has ever made. To understand these jets, we first have to look at their engines, black holes, especially the supermassive ones at the centers of galaxies. When gas and dust spiral into a black hole, they don't fall straight in. They form a disk that spins at incredible speeds and heats up to millions of degrees. Magnetic fields build up and twist around this disk like a tightly wound spring. In some cases, instead of letting everything fall into the black hole, those magnetic fields channel some of the material into narrow beams that shoot out from the poles. These are the jets. And they're not just made of light. They're made of particles, electrons, protons, and sometimes entire atoms, all accelerated to near light speed and ejected in focused streams across the cosmos. These are called relativistic jets because they involve speeds close to the speed of light. When objects move that fast, Einstein's laws of relativity start to kick in. Time slows down, mass increases, light changes direction, and to an outside observer, these jets appear even more intense because of something called Doppler beaming. It's like aiming a flashlight directly at someone's eyes, except your flashlight is a cosmic cannon. These jets can be colossal. The ones coming from the galaxy M87, the same one whose black hole was imaged by the Event Horizon Telescope, stretch out more than 5,000 light-years. Some go even farther, up to 1 million light-years in length. That's 10 times the size of the Milky Way, and the beam stays tight and focused the entire way, like a laser cutting through space. But how do they stay that focused? That's still one of the great mysteries. Most explosions in space scatter in all directions, but relativistic jets hold their shape across incredible distances. It's like a fire hose that stretches across galaxies but never breaks up or loses pressure. Scientists think magnetic fields are the secret. The jets are twisted into a corkscrew shape by these fields, which keeps the particles moving in a tight line. It's one of the most efficient and controlled energy transfers in the universe. We can see these jets in more than one way. Radio waves, X-rays, and gamma rays all make them glow. Some galaxies, called radio galaxies, are famous for the huge bright tails that sit at the ends of these jets. Those lobes are like cosmic splash zones, where gas from the jets hits the ground and stretches out. From a very long way away, you can see them. These jets also shape the galaxies around them. When they punch through gas and dust, they can heat it up and blow it away, shutting down star formation. That means relativistic jets don't just light up the universe, they sculpt it. They control how galaxies grow, how stars are born, and where matter ends up. These jets sometimes point straight at Earth. This kind of planet is known as a blazar. These beams are some of the biggest and most violent energy flashes we've ever seen when they hit our devices. These are the sniper weapons of the world, and they could be dangerous if they got closer. Thank goodness, the ones that are aimed at us are a long way off. Jets don't just come from supermassive black holes. They can also shoot out from smaller black holes, neutron stars, and even young stellar systems. But the ones powered by supermassive black holes are the largest and most energetic by far. How exactly does a spinning black hole launch a jet? What makes one black hole produce a jet and another stay quiet? Why are some jets stable while others wobble or break apart? These are active areas of research. New telescopes and simulations are helping us get closer to the answers. The Big Bang, the original explosion of everything. About 13.8 billion years ago, there was no time, space, stars, planets, or atoms. After that, everything changed in a split second. The universe grew from being too small, too thick, and too hot to be possible to the huge, cold universe we see now. The Big Bang is the name for that event, and even though the name makes it sound like a space blast, it was actually something much stranger. The Big Bang didn't happen in one spot. It didn't blow up inside a black void or fireball in the sky. It happened everywhere at once. Because before the Big Bang, there was no where. There was no space to explode into. The Big Bang created space itself, along with time and everything we now call matter and energy. It was the birth of reality. In the first tiny fraction of a second, less than a billionth of a billionth of a billionth of a second, the universe went through a period of insane expansion called inflation. During this time, it grew faster than the speed of light. And no, that doesn't break any laws of physics. Space itself can expand faster than light because it's not a thing moving. It's the thing everything else moves through. After inflation stopped, the universe was a super-hot soup of energy and particles. There were no atoms yet, just raw ingredients, quarks, electrons, and photons bouncing around in a dense fog. As the universe expanded, it cooled. After a few minutes, protons and neutrons started to form. These came together to make simple nuclei, mostly hydrogen and helium. But it wasn't until about 380,000 years later that the first atoms formed. That's when things cooled enough for electrons to stick to nuclei and make neutral atoms. This moment is known as recombination, and it's when light could finally travel freely through space. The fog lifted. That first light, the afterglow of the Big Bang, is still visible today. We call it the cosmic microwave background, or CMB. It's like a baby photo of the universe, showing us what things looked like when it was just 0.003% of its current age. This faint microwave light fills the entire sky and has been mapped in incredible detail. It's nearly uniform, but with tiny temperature differences that tell us how matter was clumping together in the early universe. Those clumps eventually became galaxies, stars, and planets, including Earth. But where did the Big Bang come from? That's the big mystery. Scientists have good evidence for everything that happened after the Big Bang, but what caused it is still unknown. Some think it was a quantum fluctuation, where empty space, thanks to quantum mechanics, gave birth to a universe. Others believe our universe might be one bubble in a vast multiverse, with other universes being born all the time. And then there are ideas like the cyclic model, where the universe expands and contracts in an endless cycle of big bangs and big crunches. All of space, time, energy, and matter came from this one event. The idea that the universe has a beginning was once controversial. Even Einstein didn't like it at first. But now, the evidence is overwhelming. The universe is expanding. The further away a galaxy is, the faster it's moving away from us. It's like dots on the surface of a balloon that's being blown up. Each one moves away from the others as the whole thing gets bigger. And this expansion is still happening. In fact, it's speeding up thanks to a mysterious force called dark energy. That means the universe isn't just coasting along. It's accelerating, stretching space faster and faster as time goes on. One day, distant galaxies will be so far away, their light will never reach us. We'll be surrounded by darkness, unaware of the Big Bang's wider aftermath. Dark energy, the force pushing the universe apart. In the late 1990s, two teams of astronomers made a discovery that stunned the scientific world. They were studying distant supernovae, exploding stars used to measure how fast the universe is expanding. The goal was to find out if gravity was slowing the expansion down. Instead, they found the opposite. The universe wasn't just expanding, it was speeding up. Something was pushing everything apart, faster and faster. That mysterious something became known as dark energy. We can't see dark energy. We can't touch it, detect it directly, or put it in a lab. But it's there. It makes up around 70% of the entire universe. All the stars, galaxies, planets, and gas clouds you can see, they're only about 5%. Even dark matter, which is itself invisible, makes up another 25%. The rest is this unknown force that fills space and drives galaxies away from each other faster and faster. So, what is dark energy? We don't know exactly, but the leading idea is that it's a property of space itself. In simple terms, space isn't empty. Even in a vacuum, where there are no atoms, no light, nothing, there's still a tiny amount of energy. This vacuum energy could act like a kind of pressure that works in reverse. Instead of pulling things together, it pushes them apart. And as space expands, there's more of it, so the force gets stronger over time. That's why the universe is getting bigger faster. There is more dark energy when there is more room. As it goes, it's like an engine that can't be stopped. It keeps going faster and faster. Einstein used the term cosmological constant in some of his equations, which gives us another idea. He used it to stop the universe from growing before we knew it was. In the end, he said it was his biggest mistake. He may have been right, but for the wrong reason. That steady thing could be dark energy, which has always been a part of space-time. Some scientists think dark energy might not be constant at all. It could be changing over time, or it might be connected to a strange, unknown kind of field that fills the universe. This idea is called quintessence. It's a dynamic form of energy, different from anything we've ever observed. Whatever dark energy is, it's powerful. Not in the explosive sense, like a supernova or black hole. It's a quiet power, a gentle but relentless push that adds up across billions of light years. And it's reshaping the future of everything. If dark energy keeps accelerating the expansion, then in billions or trillions of years, galaxies will drift so far apart that light from them will never reach us. The night sky will go dark. Eventually, even the closest galaxies will disappear from view. Future observers, if any exist, will see only blackness and their own galaxy, with no clue that the universe ever held anything more. Some theories go even farther. If the force of dark energy keeps increasing, it could eventually overcome gravity itself. Stars would fly apart. Planets would tear away from their suns. Even atoms might rip apart in a final cataclysm called the Big Rip. We don't know if that will happen, but it's a real possibility based on the math. Dark energy makes it harder for us to understand how the world started. If everything was being pushed apart, how did galaxies form? After all these billions of years, why does dark energy still seem to be the most important thing? Is it something that was always there, or did it turn on? Some things are still not clear. To solve them, scientists are building powerful tools. The Euclid Space Telescope, launched by the European Space Agency, and the Nancy Grace Roman Space Telescope from NASA are both designed to map the universe in detail, tracking how galaxies have moved over time. They're looking for clues in how dark energy has changed, if it has, and how it affects the overall shape and fate of the universe. It's odd to think that the most powerful force in the world is something we don't fully understand. It doesn't shine. It doesn't pull you in. It doesn't seem to interact with matter at all. It still has power over the future, though. What's moving the stage around behind the scenes, long after the players have left? It's the quiet puppeteer. The most massive galaxy clusters, cosmic cities of gravity. Picture a city, not just any city, but the biggest one you can imagine. Now replace its buildings with entire galaxies, its streets with rivers of dark matter, and its atmosphere with clouds of superheated gas glowing in X-rays. That's a galaxy cluster. These aren't just groups of stars. They are the universe's largest gravitationally bound structures, colossal communities of galaxies that can span millions of light years and weigh quadrillions of times more than the Sun. And among them are true giants. Some of the most massive galaxy clusters ever discovered, like El Gordo, Phoenix, and Abell 2744, aren't just heavy. They're cosmic powerhouses, shaping the very structure of the universe around them. A galaxy cluster can contain hundreds or even thousands of galaxies, but the galaxies themselves only make up about 5% of a cluster's mass. The rest? Around 10% is superhot gas that fills the space between galaxies. Gas so hot it glows in X-rays. And a staggering 85% is dark matter, the mysterious invisible substance that holds everything together with its gravity. Think about how much energy it takes to hold all of those things together. Gas, dark matter, planets, and so on. These groups look like the pinnacle of gravity's work. Some are so big that they bend space around them, which is known as gravity lensing. If you look at the sky, you can see arcs, marks, or even rings of light made by light from galaxies behind the cluster. Not only is it pretty, but it also lets us see the dark matter that is forming the cluster. El Gordo, which in English means the fat one, is one of the most well-known cases. 1/7 of a billion light-years away, it weighs about 3 quadrillion times as much as the Sun. There is a 3 after the 15 zeros. It's actually two groups crashing into each other at very high speeds. The collision is still going on and is heating up the gas, bending space, and sending shock waves through the universe. Then there's the Phoenix cluster. It's a paradox. Usually, the hot gas in clusters prevents new stars from forming by heating everything up. But in Phoenix, the gas is cooling so fast that the central galaxy is pumping out hundreds of new stars every year. That's a mystery because it challenges the usual rules about how clusters regulate themselves. Something unusual is going on, and scientists are still trying to figure out what. Another behemoth, Abell 2744, is often called Pandora's cluster. It's a cosmic train wreck, a combination of 4 different galaxy clusters that collided over billions of years. It's one of the most complex structures ever observed. Each of its parts moves differently, and its dark matter is scattered in ways that defy easy explanation. It's not just massive, it's messy. And from that mess, we learn how galaxies grow, how matter behaves, and how gravity sculpts the universe. Galaxy clusters also give us a window into the early cosmos. Light from the most distant clusters takes billions of years to reach us, meaning we're seeing them as they were long ago. By studying faraway clusters, we can understand how structure formed in the young universe, how galaxies grouped together, and how the web of matter evolved into what we see today. They also help us test dark energy. By counting how many clusters exist at different times in cosmic history, scientists can figure out how fast the universe is expanding and whether that speed has changed. Since galaxy clusters are the biggest clumps of matter, they're the perfect tool for tracking the effects of dark energy on cosmic growth. These clusters are still changing. Galaxies inside them collide, merge, and cannibalize one another. Some get torn apart. Others form new stars from gas stolen in the chaos. The intra-cluster gas, super hot and full of heavy elements, gets stirred by jets from black holes, shockwaves from collisions, and turbulence from cosmic weather. There is action on an unimaginable scale inside these cosmic cities. Whole galaxies are thrown around like rocks. Huge clouds of plasma are where stars are born and where they die. Black holes explode, then go quiet for a while. What we see in the night sky is only a small part of what is out there. Dark matter shapes it all, and gravity holds it all together. The bullet cluster, a snapshot of a high-speed galactic collision. If you look at the bullet cluster at first, it might seem like just another group of galaxies moving through space. In fact, it's one of the strangest and most important cosmic crashes we've ever found. About 3.8 billion light-years away, two galaxy groups are crashing into each other very hard. This event not only shows us galaxies in motion, but it also lets us see the unseen side of the universe. It's a very strong sign that dark matter exists. Here's what we're looking at. Two enormous galaxy clusters, each containing hundreds of galaxies, clouds of superhot gas, and massive amounts of dark matter. At some point, these two clusters slammed into each other at a speed of around 4,500 kilometers per second. That's over 16 million kilometers per hour. The smaller cluster punched through the bigger one like a bullet, hence the name. But the story isn't just about speed. It's about what happened during and after the impact. When the two clusters collided, the galaxies themselves passed through each other mostly untouched. That's because galaxies are made up of so much empty space that the stars rarely hit one another. It's like two swarms of bees flying through each other with almost no collisions. The hot gas, however, didn't get off so easily. It makes up most of the normal matter in the clusters and interacts like smoke or fog. When the gas clouds met, they slammed together, slowed down, and got stuck between the two clusters. This gas is so hot, millions of degrees, that it glows in X-rays, and we can see it clearly with telescopes like Chandra. When scientists used gravitational lensing to map where the mass in the bullet cluster actually is, they found something surprising. The gravity didn't come from where the hot gas was. It came from where the galaxies had gone, past the gas and through the other cluster. That means most of the mass moved with the galaxies, not the gas. But remember that most normal stuff is gas. What then was pulling all that weight? Dark matter is the way. The bullet cluster is like an X-ray for the universe. It separates matter that can be seen from mass that can't be seen. Dark matter doesn't interact with other things like gas does, so it, like the galaxies, goes right through the crash. It didn't stop or slow down, it kept going, and the mark of its gravity was still there. This single observation became one of the strongest arguments that dark matter is real, and not just a trick of gravity, or a mistake in our equations. If gravity alone were causing the behavior of the hot gas, the lensing map wouldn't match what we see, but it does. Perfectly. This tells us there's something massive there that we can't see, touch, or detect directly. It only shows itself through gravity. The bullet cluster also helps us understand how fast dark matter particles move, how they cluster together, and how they behave under extreme conditions. Whatever dark matter is made of, it's not like regular matter. It doesn't collide, it doesn't heat up, it doesn't glow, it's just there, massive, silent, and dominant. Even beyond dark matter, the bullet cluster is just an incredible cosmic event. Think about the scale. 2 entire clusters, each filled with thousands of galaxies and weighing more than 250,000,000 suns, colliding like slow-motion wrecking balls. The aftermath stretches across millions of light-years and continues to evolve today. This collision isn't just a fluke either. We've found other clusters that show similar separations between gas and mass, though none as clean and dramatic as the bullet cluster. That's why it remains the poster child for cosmic collisions, a smoking gun captured in mid-blast. Scientists continue to study it with new tools and telescopes, hoping to refine our understanding of dark matter. Could this reveal new particles? Could it show us cracks in our current physics? Could it eventually lead us to the long-sought dark sector, the part of the universe that makes up 85% of its matter, yet remains invisible to our eyes? The strong nuclear force, the force that binds the universe together. There is a strong radioactive force that holds everything together. You can't feel it, see it, or even know it's there. Not a star, not an atom, not you. This is the atomic core, which is so small that it makes molecules look huge. It's where the most powerful force in the world acts. Every atom has a nucleus made up of protons and neutrons. Protons have a positive charge, and as you probably know, like charges, repel. So why doesn't the nucleus just explode from the inside out, as all the protons push away from each other? The answer is the strong nuclear force. This force is what keeps protons and neutrons locked tightly together. It's incredibly powerful, about 100 times stronger than the electromagnetic force that pushes the protons apart. But it only works at an incredibly short distance, about the width of a proton itself, or 1 femtometer. If two protons get just slightly farther apart than that, the strong force disappears and the repelling takes over. The strong force is so intense that it doesn't just bind protons and neutrons together, it actually creates them. Inside each proton and neutron are even smaller particles called quarks. Quarks are held together by particles called gluons, the messengers of the strong force. Think of gluons as tiny, invisible springs, tying quarks together so tightly that no one has ever seen a single quark alone. They always come in groups, never solo. This property is called confinement, and it's one of the most extreme behaviors in all of physics. Try to pull a quark out of a proton, and the strong force reacts by creating more quarks. It's like trying to stretch a rubber band that gets stronger the more you pull it, until it snaps and forms a new band instead of breaking completely. Take a step back and zoom out to the level of atoms and stars. Not only does the strong nuclear force keep atoms together, it also gives them power. In the heart of the Sun, hydrogen atoms are smashed together to make helium. This is known as nuclear fusion. Einstein's famous equation, E equals sine mc2, says that when protons merge, a small amount of mass is turned into energy. That power is the sun's rays on your skin. Nuclear fusion would not happen without the strong force. The sun wasn't shining. There would be no life as we know it. Nuclear fusion doesn't just power stars. It builds the elements of the universe. Lighter elements like helium, carbon, and oxygen are made in stars. Heavier ones like gold and uranium are created in supernovae or neutron star collisions. All of these processes rely on the strong force to fuse atomic nuclei, or to hold them together during violent explosions. The strong nuclear force also determines how stable an atom is. If an atom's nucleus has too many protons or neutrons, the balance of forces tips, and the atom becomes radioactive. It may emit particles or energy to try to stabilize itself. That's nuclear decay, and it's what powers nuclear reactors and atomic bombs. Again, it's the strong force that makes this possible by setting the rules of the nucleus. And what about the beginning of the universe? Since the world was so hot and full of energy right after the Big Bang, there were no atoms. Quarks and gluons were free to move around in quark-gluon plasma, which is like a soup made of space particles. It got cooler in the universe, and the strong force locked quarks into protons and neutrons. Matter as we know, it would not have formed without that freezing process. Scientists are still exploring the strong nuclear force in experiments like those at CERN and Brookhaven's RHIC Collider. By smashing heavy ions together at nearly light speed, they recreate conditions from just after the Big Bang, briefly forming quark-gluon plasma and watching how it behaves. These high-energy collisions help us study confinement, nuclear matter, and the limits of this powerful force. The strong force is also incredibly non-linear, meaning it doesn't act in predictable ways like gravity or magnetism. If you double the distance between two masses, gravity becomes 4 times weaker, but with the strong force, the rules are strange. It doesn't fall off gradually, it just shuts off, and within its tiny range, it becomes overwhelming. The strong nuclear force works in a world that is too small for us to see, but it has effects all over the place. It keeps atoms together. The stars need it. It shaped the things that make up your bones, your blood, and the ground you walk on. It holds everything together, stronger than anything else, but only found in the smallest spaces of reality. The Sun's core, a constant thermonuclear furnace. Something amazing is happening 93 million miles away right now. It's happening all the time, in silence, and with unimaginable power. There is a nuclear fire so hot that it lights up the whole solar system deep inside the Sun, in the center. This fire is smashing atoms together. This is the center of the Sun, a hot ball of plasma where energy is made from matter all the time. Earth would be a frozen rock without it. It makes life possible. The Sun's core is about 20% of the Sun's total size, but it contains more than half of its mass. It's the most extreme environment in our solar system. Temperatures reach about 15 million degrees Celsius. That's over 27 million degrees Fahrenheit. And the pressure is more than 250 billion times greater than Earth's atmosphere. If you could somehow stand in the core, you'd be crushed and vaporized instantly. At these temperatures and pressures, the atoms of hydrogen, the most basic element in the universe, don't act like they do on Earth. They're stripped of their electrons and smashed together with such force that their nuclei fuse. This process is called nuclear fusion, and it's what powers the Sun. Here's how it works. 4 hydrogen nuclei, protons, fuse together to form one helium nucleus. But the helium weighs just a little less than the 4 protons combined. That missing mass doesn't disappear. Instead, it gets converted into energy, thanks to Einstein's famous equation, E equals mc squared. And even though the mass loss is tiny, the amount of energy released is enormous. And this isn't happening just once. The Sun fuses about 600 million tons of hydrogen into helium every second. In that time, it converts about 4 million tons of mass directly into energy. That energy travels outward through the layers of the Sun, eventually reaching the surface and radiating into space as sunlight, heat, and solar wind. But the journey from the core to the surface is long and slow. After fusion occurs, the energy produced, mostly in the form of gamma rays, has to travel through the Sun's radiative zone, where it's constantly absorbed and re-emitted by particles. This random walk can take up to 1 million years before a single photon escapes to the surface. From there, it only takes about 8 minutes to reach Earth. So, how about the Sun you feel today? That power came from the Sun's core 1 million years ago. Neutrinos are tiny particles that have almost no mass and don't interact much with matter. They are also made during fusion. You don't even notice how many trillions of them go through your body every second. But we need to know them in order to understand what's going on inside the Sun. Scientists have proven that fusion is happening right now by finding these neutrinos from the Sun. The Sun's core isn't just a power source, it's a natural nuclear reactor. And unlike fission, which breaks atoms apart and is used in nuclear power plants on Earth, fusion combines atoms. It's cleaner, more efficient, and, if we can harness it, could be the future of energy for us too. But replicating the Sun's core conditions in a lab is one of the biggest challenges in science. The balance inside the core is delicate. Gravity constantly pulls the Sun inward, trying to collapse it. But the outward pressure from the energy created in the core pushes back. This balance, called hydrostatic equilibrium, keeps the Sun stable. If fusion stopped, the Sun would collapse under its own weight. If fusion grew too strong, it would expand and overheat. It's a perfect tug-of-war that's lasted billions of years. That being said, how long will it last? The Sun is about 1/2 of the way through its 4.6 billion year life. Fusion can go on for another 5 billion years or so because it still has enough hydrogen in its core. The core will shrink and heat up, though, when the hydrogen runs out. This will begin a new phase where helium is formed into stronger elements. That change will make the Sun a red giant, which means it will grow and finally swallow up Mercury, Venus, and maybe even Earth. Eventually, the core will no longer support fusion, and the Sun will shed its outer layers, leaving behind a hot, dense remnant called a white dwarf, a stellar ember glowing quietly for billions of years more. Solar flares and coronal mass ejections, explosions from our star. From above, the Sun may look quiet and steady, but its surface is anything but. It explodes every once in a while with an explosion so big that it can send billions of tons of matter into space, damage satellites, knock out power lines, and even create beautiful auroras. This kind of blast is known as a solar flare, or a coronal mass ejection, CME. They are two of the strongest and most intense things that can happen in our solar system. A solar flare is a sudden, intense burst of radiation coming from the Sun's atmosphere. It's like a massive flash of light and energy triggered by twisted magnetic fields near sunspots, dark, cooler regions on the Sun's surface caused by magnetic activity. When these magnetic fields get tangled and stressed, they can snap and reconnect, releasing an enormous amount of energy in the process. Solar flares are the solar system's version of a lightning strike, but on a cosmic scale. In just a few minutes, a flare can release as much energy as billions of hydrogen bombs. This energy spreads across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. The most powerful flares can be seen as sudden bright flashes on the Sun's surface and detected by space observatories that constantly monitor solar activity. These flares are classified by strength. The weakest are A-class, followed by B, C, M, and finally X-class, the strongest. Each class is 10 times more powerful than the one before it. An X10 flare, for instance, is 10 times more intense than an X1. The biggest solar flare ever recorded, in 2003, was so strong it maxed out the sensors and is estimated to have been X45, an energy release so intense it disrupted communications on Earth and damaged satellites. These days, solar flares are mostly about power and wave energy. Things are even more dangerous when they happen with a coronal mass ejection. A CME is a huge ball of plasma and magnetic field that is thrown into space. Imagine that the Sun is spewing out billions of tons of charged particles that are moving at up to 3,000 kilometers per second. Because Earth has an atmosphere and magnetic field, these particles don't pose a threat to people. However, they can damage satellites, space stations, and even power lines. When a CME hits Earth, the charged particles interact with our planet's magnetic field. This can cause geomagnetic storms, huge disturbances in Earth's magnetic environment. The stronger the storm, the more likely it is to cause blackouts, disrupt GPS, interfere with radio signals, and damage electrical transformers. One of the most famous examples is the Carrington event in 1859, when a powerful CME caused telegraph systems to spark, catch fire, and fail across continents. If something similar happened today, it could cost trillions of dollars in damage. However, not all CMEs are bad. They also cause auroras, which are the beautiful northern and southern lights, when they hit. These lights happen when charged particles from the Sun hit atoms in the high atmosphere of Earth. This makes the atoms glow greatly. Auroras can be seen much farther from the poles than normal during strong solar storms. Sometimes they can even be seen in humid areas. Solar flares and CMEs often happen together, but not always. A flare can occur without a CME, and a CME can blast off without a noticeable flare. But when both happen in sync, and the CME is aimed at Earth, the effects can be felt across the globe, and even beyond it. Astronauts in space need protection, airlines may reroute polar flights, and ground systems have to be put on alert. So how do we prepare for them? Scientists use satellites like SOHO, SDO, and Parker Solar Probe to watch the Sun 24/7. When a flare or CME is detected, space weather alerts are issued, giving Earth a few hours to a couple of days' notice, depending on the speed of the ejection. That time can be crucial for turning off sensitive electronics or preparing spacecraft for impact. What exactly triggers the biggest flares? Why are some CMEs so much faster and stronger than others? Can we predict when a sunspot is about to explode? These questions are driving new missions and research, including the effort to understand how the Sun's magnetic fields behave deep beneath its surface. Tidal forces near black holes. Spaghettification in action. If you ever fell into a black hole, and let's be clear, you should absolutely not try, you'd encounter something far stranger than just darkness or crushing gravity. You'd experience one of the weirdest and most extreme effects in the universe, spaghettification. That's not a joke, it's a real scientific term, and it's caused by tidal forces near a black hole. Tidal forces are the result of gravity pulling more strongly on one side of an object than the other. You can see a mild version of this on Earth. The moon pulls on our oceans, creating tides. That's because the side of Earth facing the moon is slightly closer and feels a slightly stronger pull than the far side. The result is a stretch in the water. Think about that effect 1 billion times stronger. Gravity pulls things closer to a black hole so fast and over such a short distance that it spreads things vertically and squeezes them horizontally. This is called spaghettification. And it means that your body is being stretched into a long, thin string of atoms. No matter which way you fall, head first or feet first, the end that is closer to the black hole gets a much stronger pull than the other end, which pulls you apart. For a small black hole, the tidal forces are so strong near the event horizon, the boundary beyond which nothing can escape, that you'd be torn apart before you even reach it. For a supermassive black hole, like the one at the center of our galaxy, the event horizon is much farther out. So theoretically, you could fall through it without immediate harm, until you get closer to the singularity at the center, where tidal forces grow infinite. Spaghettification doesn't just apply to people. Stars, too, can get caught in this deadly trap. When a star passes too close to a black hole, it can be tidally disrupted, ripped apart by gravity. The black hole tears the star into a long stream of gas, some of which gets flung away, while the rest swirls into a glowing disk around the black hole. These events are called tidal disruption events, TDEs, and they've been observed by telescopes on Earth and in space. For a few weeks or months, the shredded star shines brilliantly as its remains spiral inward. Tidal forces also warp space and time. As you fall closer to a black hole, time slows down relative to someone farther away. From your perspective, you'd fall normally, but to a distant observer, you'd appear to slow down, stretch out, and freeze right at the event horizon. Your light would become redder and dimmer until it faded completely. This is called gravitational time dilation, and it's a real consequence of Einstein's theory of general relativity. Inside the event horizon, all paths, forward, backward, up, down, lead to the singularity at the center. It's a one-way trip. Once inside, you cannot escape no matter what. Tidal forces will compress you into nothingness, squeezing all your atoms together in a place where our laws of physics stop making sense. We don't even know what exists at the singularity. It could be a point of infinite density or a door to something else entirely. No one knows, because nothing that falls in can ever get back out to tell us. That's part of what makes tidal forces near black holes so terrifying and so fascinating. They're not just stronger than anything we experience on Earth. They're beyond anything we can fully model. We use equations, simulations, and images to get close. But the truth is that the inside of a black hole, shaped by these unimaginable forces, remains one of the greatest unknowns in science. There are more unusual versions of this idea in some theories, like spinning Kerr black holes or charged Reisner-Nordstrom black holes, where the tidal forces might act in different ways or even let there be white holes or wormholes on the other side. But those are still just ideas. Spaghettification is still thought to be the most likely result for anything brave or unlucky enough to fall in. Antimatter explosions, energy from matter's evil twin. Picture touching something and quickly turning it into pure energy. None left over, don't smoke. A flash of power so strong that it could destroy everything in its path. It happens when matter hits antimatter, which is the opposite of matter. There's more than just science fiction. It's true. It is one of the strongest and most efficient blasts in the world when matter and antimatter hit each other. Every particle of matter, protons, electrons, neutrons, has a mirror image twin with opposite charge. These are antiparticles, The antiparticle of an electron is called a positron. It has the same mass, but a positive charge. A proton's antiparticle is called an antiproton, with a negative charge. Put a particle and its antiparticle together, and they don't just cancel out, they annihilate. In that annihilation, all their mass is converted into energy. No ash, no debris, just a burst of pure energy, often in the form of high-energy gamma rays. Compare that to chemical explosions, like TNT or gasoline, which only convert a tiny fraction of mass into energy. Matter-antimatter annihilation is 100% efficient. It's the ultimate fuel, if you can find it, or make it. So why don't we see antimatter everywhere? Because when the universe began with the Big Bang, matter and antimatter were created in nearly equal amounts. But for reasons we still don't fully understand, something tipped the scales. Somehow, matter won. For every billion pairs of particles that annihilated, one particle of matter was left behind. That leftover matter became the stars, planets, and people we see today. The antimatter mostly vanished, wiped out in the universe's first great explosion. Tiny bits of antimatter exist. Scientists have created antiparticles in particle accelerators, like the Large Hadron Collider, LHC. Positrons are used in PET scans in hospitals to detect cancers. We've even created antihydrogen, an atom made of a positron and an antiproton, though only for tiny fractions of a second before it disappeared. If you had just 1 gram of antimatter and mixed it with 1 gram of matter, the resulting explosion would release about 90 trillion joules of energy. That's roughly the same as a 20-kiloton nuclear bomb, the kind dropped on Hiroshima, from just a spoonful. So it's not shocking that science fiction writers love the idea of antimatter. People have thought of it as a way to travel, power starships, or a weapon that could end the world. But in real life, the problems are very big. It is very hard to make antimatter. Only a few nanograms have been made so far. Care must be taken to store it. It can't touch anything made of matter, like any container we've ever made, or it will destroy it right away. Scientists use magnetic fields to suspend antiparticles in a vacuum, creating tiny traps that hold them in mid-air. Even then, they can only store antimatter for a short time. The tiniest contact with regular matter ends in a flash. That makes antimatter expensive. Producing just 1 gram would cost billions of dollars with today's technology. But antimatter isn't just about power or weapons. It's also a tool for science. Physicists use it to study the laws of the universe, to test CPT symmetry, which says the laws of physics should be the same for particles and antiparticles, and to explore why the early universe ended up with more matter than antimatter. These questions go to the heart of why anything exists at all. There's also a chance that natural antimatter exists in space. Strange gamma-ray signs come from some parts of the galaxy, which may be caused by positron-electron annihilation. Are there stars that don't matter? Galaxies made of antimatter? Most experts say no, because where matter and antimatter meet, there would be a lot of blasts. Still, some people look anyway, just in case. And here's a final twist. Antimatter could be a beacon. If we ever detect a stream of positrons or antiprotons coming from a distant star system, it might not be natural. It might be artificial, a signal from an advanced civilization using antimatter power. Additionally, antimatter has the potential to serve as a lighthouse. Positrons or antiprotons coming from a faraway star system might not be normal if we ever find them. It could be a fake broadcast from a highly advanced race that uses antimatter power. The most powerful supercomputers simulating the universe. It's easy to forget that the world has rules when you look up at the stars. Physics tells us that everything moves, has mass, and has energy. The rules are very complicated and cover a huge area, so our brains can't fully understand them. That's where very powerful computers come in. Not only do these robots do math, but they also make reality. That's a lot of power. The world's most powerful supercomputers are being used to model whole universes. Simulating the universe doesn't just involve rendering a pretty picture of galaxies. It means using physics equations to mimic how the universe actually formed, from just after the Big Bang all the way to the present. It includes gravity, dark matter, dark energy, gas dynamics, star formation, black holes, and cosmic radiation. And it must track the positions and behavior of billions of virtual galaxies, each with their own billions of stars. Doing this requires computers far beyond anything we use at home or in offices. We're talking about systems with hundreds of thousands of processors, running continuously for weeks or months. These are supercomputers like Frontier in the United States, Fugaku in Japan, Summit, Perlmutter, and Cosma. Machines capable of performing quadrillions of calculations per second. That's a 1 followed by 15 zeros. The Illustris project is one of the most well-known cosmic models. This simulation began in 2014 and models a cube of the universe that is 350 million light-years across. Over 13 billion years of cosmic development, it used 12 billion 3D images, or resolution elements, to show how gas cooled, stars formed, black holes grew, and galaxies crashed into each other. Then came Illustris, an upgraded version with even better physics, higher resolution, and more realistic results. It produced stunning 3D maps of cosmic structures, clusters, voids, filaments, all matching what we see through telescopes. The beauty of it, we can test ideas. What happens if dark energy is stronger, if galaxies form faster? The simulation answers by showing us what the universe would look like under those conditions. Another heavyweight is the Millennium simulation, created by the Max Planck Institute. It followed the evolution of 10 billion particles representing dark matter, starting shortly after the Big Bang. The result was a giant map of the invisible scaffolding of the cosmos, those filament-like structures that form the cosmic web. Why is this so powerful? Because we can't rewind the real universe. We can't recreate a galaxy or rerun the Big Bang in a lab. But with simulations, we can. If observations from telescopes don't match the simulation, we know our model is missing something. That leads to better theories, better predictions, and sometimes even new physics. Supercomputers have also helped us understand black holes. The Event Horizon Telescope, which captured the first image of a black hole in M87, used petabytes of data, collected from observatories around the globe, and needed advanced computing to reconstruct the final image. It wasn't just a photo. It was a digital recreation built by processing signals that took millions of lines of code to interpret. And it doesn't stop there. Today's simulations also explore the early universe, the formation of the first stars, the merging of neutron stars, the behavior of dark matter, and the effect of massive black hole jets on galaxy growth. Some even simulate what would happen if the laws of physics were slightly different, giving us a glimpse into alternate universes that might have formed with just a tweak in gravity or particle mass. But it's not just about astronomy. Simulating the universe helps us understand the limits of computation itself. These supercomputers push the boundaries of what machines can do. They require new algorithms, smarter ways to handle data, and software that can distribute tasks across thousands of CPUs and GPUs without crashing. It's science meeting engineering at its highest level. In fact, the tools developed for cosmological simulation often spin off into medicine, climate modeling, or energy research. When you simulate a galaxy, you're not just building a picture. You're building an engine for discovery that can be applied across fields. The LHC and future colliders are attempts to create cosmic power. Near the border between Switzerland and France, deep underground, there is a machine that is so powerful that it can replicate the world as it was minutes after the Big Bang. The Large Hadron Collider, or LHC, is the biggest and strongest particle collider that has ever been built. It does more than just smash things, though. It breaks apart matter into its building blocks, showing the forces and particles that formed the early universe. It's only the beginning. The LHC is a 27-kilometer ring buried about 100 meters below ground. Inside that ring, particles, usually protons, are accelerated to nearly the speed of light using magnetic fields. Then, they're smashed head-on into each other. When they collide, their kinetic energy is so high that it's converted into mass and new particles, according to Einstein's famous equation E = mc2. But these aren't just explosions. They're tiny, controlled experiments. The debris from each collision is recorded by massive detectors, some as large as buildings, filled with sensors, magnets, and computers. Scientists sift through these collisions, looking for traces of exotic particles, new forces, or cracks in our current understanding of physics. In 2012, the LHC made headlines around the world by discovering the Higgs boson, a particle predicted decades earlier that helps explain why other particles have mass. Without the Higgs, the universe wouldn't hold together. Finding it was like discovering the final piece of the puzzle in our model of fundamental physics. It has probed the behavior of quark-gluon plasma, a superhot state of matter believed to have existed just microseconds after the Big Bang. It's also searched for supersymmetry, extra dimensions, and dark matter candidates, so far without success. But even not finding something tells us what's possible and what's not. Every result narrows the path to deeper truths. Yet even the LHC has its limits. Its highest collision energy, 13.6 trillion electron volts, TeV, is tiny compared to what happens naturally in space. Some cosmic rays hit Earth's atmosphere with millions of times more energy. So scientists are already planning the next generation of colliders, machines that will go bigger, faster, and deeper. The Future Circular Collider, FCC, is one of the most bold ideas. It was planned by CERN and would be 100 kilometers across, which is almost 4 times the size of the LHC. It could reach energies of 100 TeV or more. That's enough to try whole new areas of physics. We might find out what dark matter is made of, whether quantum gravity exists, or if there are unknown particles outside of the standard model. China is also developing its own version, the CEPC, Circular Electron Positron Collider. Initially planned to study the Higgs boson in extreme detail, it could later be upgraded to smash protons at record-breaking energies. These machines are billion-dollar bets, but with the potential for trillion-dollar answers. And it's not just about size. New technologies are being tested to create plasma wakefield accelerators, which use waves of energy in plasma to push particles to high speeds over much shorter distances. These could one day shrink a collider to the size of a room while matching the LHC's power. So, what's the point of all this? Because we don't just want to know what the universe is made of, we want to know why. Why is gravity so weak compared to the other forces? Why is there more matter than antimatter? Why does dark energy exist? Why are the constants of nature what they are? We have guesses. But to know for sure, we need to recreate the conditions that existed when everything was new. And that means smashing things, at speeds and energies that mimic creation itself. Colliders like the LHC are time machines. They don't let us go back, but they let us recreate the past, one subatomic collision at a time. They're also microscopes, showing us what's inside protons, neutrons, and even empty space. And they're crystal balls, helping us predict how the universe might behave in ways we've never seen. Thermonuclear runaways on neutron stars, type 1 X-ray bursts. A teaspoon of a dead star that is as thick as a city and weighs as much as a rock. Imagine a tiny bit of gas falling on it. That tiny bit of gas sets off a blast that is strong enough to give off more energy in seconds than the sun does in a whole day. That's the scary truth about a type 1 X-ray burst, which is an explosion in space that happens on the surface of a neutron star during a process called thermonuclear runaway. A neutron star is what's left behind after a massive star dies in a supernova. What remains is a compact, ultra-dense ball made almost entirely of neutrons. These stars are small, just about 20 kilometers wide, but they pack more mass than our entire sun. Their gravity is so intense that anything falling toward them crashes at nearly light speed. You can't land gently on a neutron star. You splatter hard. Now picture a neutron star that is part of a binary system, which means it is close to another star. When the neutron star gets close enough, it starts taking gas from the star next to it. Most of the gas in this spiral is hydrogen and helium. It builds up on the neutron star's surface into a thin layer. Because the star has such strong gravity, this layer gets thicker, hotter, and more squeezed over time. The bottom layer of this gas becomes so hot and dense that nuclear fusion kicks off. But it doesn't start gradually. It happens all at once. That's the thermonuclear runaway. It's like lighting a fuse under a giant pile of fireworks. The gas ignites in a sudden flash, creating a burst of X-rays so bright it can be seen from across the galaxy. These flashes typically last from a few seconds to a few minutes and can repeat every few hours or days, depending on how fast the neutron star is feeding. The clocked burster, GS 1826-24, is one of the most well-known places where these bursts come from because it explodes almost every time. Scientists can time the flashes so that they happen at the right times every few hours. This consistency makes it possible for scientists to study high gravity, fusion, and accretion in a way that could never be done in a lab on Earth. In some rare cases, the bursts don't stop at the surface. If the initial explosion is powerful enough, it can cause the outer layers of the neutron star to expand rapidly, almost like the star is breathing out. For a moment, the radius of the star increases, cooling the emission slightly before it collapses back down and finishes the flash. This is called photospheric radius expansion, and it allows scientists to estimate the neutron star's size and even its distance from Earth. Despite being some of the most powerful events in the universe, Type 1 X-ray bursts are still a mystery in many ways. Scientists debate how deep the fusion goes, whether heavier elements form in the blast, and how the bursts affect the long-term behavior of the neutron star. Some believe that repeated bursts could gradually strip away the neutron star's atmosphere, while others think it helps maintain a balance in the accretion process. Newer observations using space telescopes like NICA, Integral, and Chandra are giving us better data than ever before. These instruments can detect not just the brightness of the bursts, but also their spectra, essentially a fingerprint of the elements involved. This has revealed strange things, like ashes of nuclear fusion being mixed into the atmosphere, or brief appearances of rare elements like nickel and carbon. But you can't always count on it. Some bursts act in strange ways. Some neutron stars have been seen to explode in superbursts instead of short, sharp flashes. These are huge blasts that last hours and send out 1,000 times more energy than a normal X-ray burst. Carbon fusion is thought to be involved deeper below the surface, but no one knows for sure what sets them off. One star, 4U 182030, located in the dense globular cluster NGC 6624, has shown both regular and superburst activity. Incredibly, it's in a system where the neutron star is stealing gas from a white dwarf, meaning the gas it pulls in is almost pure helium. That changes the chemistry of the bursts, offering scientists a rare peek at how different fuel types influence runaway fusion. Why is this all so important? Because these bursts let us study nuclear physics in a way that we can't do on Earth, under gravity. Explosions are like nature laboratories that show how matter acts when it is pushed to the limits of science. Astronomers can test Einstein's theory of general relativity by looking at when and how strong the bursts are. This is possible because neutron stars have very strong gravity that bends light and time. Galactic winds, when entire galaxies blow material into deep space. Take a mental picture of a galaxy breathing out and sending a strong wind into space that blows away stars, gas, and dust. That's exactly what happens during a thing called galactic winds. These aren't light waves. Matter is blasted out at hundreds to thousands of kilometers per second, and these events are very fast and very powerful. They can change the shape of galaxies. These winds have an effect on the whole world, not just one galaxy. So how do these cosmic hurricanes start? It usually begins in a galaxy packed with intense star formation, known as a starburst galaxy. These galaxies are like overworked factories, churning out new stars at breakneck speed. But stars don't live forever, especially the big ones. Massive stars live fast and die young, ending their lives in violent supernova explosions. Each supernova blasts out huge amounts of energy, heating the surrounding gas to millions of degrees. Now imagine dozens or hundreds of supernovae going off in a crowded area. That energy adds up. Eventually, it gets strong enough to push the galaxy's gas outward in all directions, like an overpressured steam valve bursting open. That's the beginning of a galactic wind. But it's not just supernovae. Black holes at the centers of galaxies, especially the monstrous ones in active galactic nuclei, AGN, can also launch these winds. As matter falls into the black hole, it heats up and shoots out powerful jets and radiation. These forces can push material outward in vast streams. In fact, AGN-driven galactic winds are some of the most powerful forces in the universe, able to reshape entire galaxies or even shut down star formation altogether. The most famous example of this is M82, also known as the Cigar Galaxy. Located about 12 million light-years away, M82 is a starburst galaxy that's ejecting material in massive plumes. Using telescopes like Hubble and Chandra, astronomers have captured images showing glowing red filaments of gas shooting out from the galaxy's center, like smoke from a chimney. These winds are carrying material out of the galaxy at speeds of over 1,500 kilometers per second. Why does this matter? Because galaxies need gas to make stars. When galactic winds blow out too much gas, they can quench star formation, basically turning off a galaxy's ability to grow. In this way, galactic winds act like regulators, preventing galaxies from becoming too big too fast. They help explain why most galaxies today aren't forming stars at the same wild pace they did billions of years ago. Galactic winds also help us figure out a mystery about the universe. Where is all the matter that is missing? Models say that there should be more gas in the universe than we can find. But some of that gas may have been pushed out of galaxies by galactic winds a long time ago and is now hiding in the huge spaces between them. To put it another way, these winds may have cleaned up the world. As these winds carry gas away, they take metals, elements like oxygen, carbon and iron, into intergalactic space. These elements are created in stars, so when galactic winds blow them out, they enrich the cosmic environment, seeding other galaxies or even forming future planets and stars. Without galactic winds, the universe might be a lot more boring and a lot less habitable. Recent research using ALMA, JWST, and XMM Newton has revealed even more about these winds. Some winds aren't smooth, they're clumpy, made up of cold gas blobs moving through hot plasma. Others show shock fronts, where fast-moving material crashes into slower gas, creating arcs of glowing light. Scientists are also studying how magnetic fields and cosmic rays might help power these winds or steer their direction. Galactic winds don't always blow everything away. This is one of the most important things we've learned in the last 10 years. They recover some of the time. It's possible that the gas will slow down, cool down, and fall back into the galaxy-like rain. A galactic spring is the name for this process that helps galaxies keep themselves in balance. It's not enough to just blow things up. You have to find a balance between what stays and what goes. Even dwarf galaxies, the small fry of the universe, can generate galactic winds, and when they do, they can lose almost all their gas in one blow. This explains why many dwarf galaxies look so empty and why they stopped forming stars early in the universe's history. Galactic winds may be most strong when they come from plumes caused by quasars. The very bright cores of galaxies with active black holes are called quasars. Astronomers saw one of these quasars blowing out gas at almost 20,000 kilometers per second in 2020. This is so fast that it could not be affected by the galaxy's gravity at all. That could mean that the galaxy will never be able to make stars again, and it will become red and dead much faster than thought. Tidal disruption events, when a star gets torn apart. Imagine a peaceful star drifting through space for billions of years, glowing steadily, minding its own business, until it wanders too close to a cosmic monster. That monster is a black hole, and what happens next is one of the most violent, terrifying, and fascinating events in the universe, a tidal disruption event, or TDE for short. In a TDE, a star is torn apart, ripped limb from limb, by the overwhelming gravity of a black hole. The star doesn't fall all at once. Instead, as it gets closer, the difference in gravity between the near side and the far side of the star becomes extreme. This is called tidal force, and it stretches the star like spaghetti. Yes, literally. Astronomers often call this process spaghettification. But before we get to the gory details, let's talk about where this happens. TDEs usually occur near supermassive black holes, which sit at the centers of galaxies. These black holes are millions to billions of times more massive than the Sun. They're invisible, but their gravitational grip extends far and wide. Most of the time, stars orbit around them at a safe distance. But every so often, a star gets unlucky. Maybe it's nudged by another star, or its orbit decays, and it gets pulled in too close. This means the star has crossed the tidal radius, which is the point where the black hole's gravity is greater than the star's own gravity. These are the first parts of the star to die. Gas starts to peel off in long streams that go around the black hole in a circle. The whole star can be torn into a bright stream of plasma that swirls around in a circle in hours or days. Roughly half of that shredded material is flung outward into space. The rest falls toward the black hole, forming a bright, hot accretion disk. This disk can shine brighter than the entire galaxy it's in, at least for a few weeks or months. That's how we spot TDEs from Earth, as sudden, powerful flashes of X-rays, ultraviolet, or visible light from the centers of galaxies. Assassin 14 Li, which was found in 2014, was one of the most well-known tidal disturbance events ever reported. Many telescopes around the world saw a galaxy far away suddenly get brighter. After a year, scientists watched as the light slowly went out, letting them see the black hole's messy feast in real time. They even found changes in the shape of the light spectrum, which told them something about how the torn star was moving and what it was made of. Another wild TDE was at 2019 KIS, dubbed the Rosetta Stone of tidal disruption events. Detected in 2019, it was caught early, just as the star was starting to rip apart. Astronomers using X-ray, radio, and optical telescopes saw the black hole not only swallow the star, but launch a powerful wind of matter outward at nearly 10% the speed of light. It was one of the clearest examples of a black hole both eating and burping in space. In 2022, a rare repeating TDE called at 2022 CMC lit up the sky like a cosmic lighthouse. This one created relativistic jets, beams of energy moving near the speed of light, shooting out from the poles of the spinning black hole. These events are incredibly rare and extremely powerful, lasting months or even years. The bright bursts of TDEs aren't just fun for observers, they're also great for science. They let us look at black holes that we couldn't see otherwise. The light graph shows how the brightness changes over time. Scientists can use this to guess the mass and spin of the black hole. Because different parts of a star burn at different speeds, some TDEs can even show information about how the star is put together. They also help test Einstein's theory of general relativity. Near the black hole, space and time are warped, and the light from the event bends and shifts in measurable ways. That makes TDEs perfect natural laboratories for studying how gravity behaves in extreme environments. But not all tidal disruption events end the same way. Sometimes a star survives the encounter, barely. These are called partial TDEs, where the star is only grazed, losing part of its mass before swinging away. It's like a near-death experience for a star, and it might happen more often than full-on disruptions. There's even a theory that some TDEs involve binary stars, pairs of stars orbiting each other. In these cases, one star is devoured while the other is flung away at incredible speed, creating a hypervelocity star that rockets out of the galaxy. These runaway stars have been observed, and some may trace their origins back to such deadly dances with black holes. Thanks to new telescopes like the Zwicky Transient Facility, ZTF, and the upcoming Vera C. Rubin Observatory, astronomers expect to find thousands more TDEs in the coming years. Each one will offer a unique glimpse into the wild feeding habits of black holes. Primordial black holes. tiny ancient engines of destruction? It is possible that creatures skulked in the shadows long before galaxies formed and stars illuminated the cosmos. Not big ones that spin, but little ones that you can't see. It's possible that these are some of the oldest and strongest things in the universe, if they even exist. They are called primordial black holes. Primordial black holes are not born the way normal black holes are. Regular black holes form when stars die and collapse under their own weight. But primordial black holes are different. They are thought to have formed just fractions of a second after the Big Bang, when the universe was still a hot, dense soup of particles. Back then, tiny changes in density could have created pockets of matter so compact that they collapsed directly into black holes, and they didn't need to be big. Some of these black holes could have had the mass of a mountain squeezed into something smaller than an atom. Others might have been as massive as a planet or a star. The range is wide and strange. What makes them so powerful isn't just their size or age, it's what they could do. A tiny black hole with the mass of a city could still tear through a planet like Earth without even blinking. It would pull matter inward with unstoppable force. And if one were to pass through Earth, it might create quakes, gravitational disturbances, or leave behind nothing but a hole in the fabric of space-time. We haven't found one yet, but scientists have been searching. One reason for the interest: these tiny black holes might solve the mystery of dark matter. Dark matter is the invisible stuff that holds galaxies together. We can't see it, but we know it's there because of how it tugs on stars and galaxies with gravity. Some scientists think that primordial black holes could make up a portion, or even all, of this hidden matter. If that's true, then primordial black holes could be scattered throughout the universe, even drifting through our own galaxy, maybe even closer than we think. In fact, researchers have looked for them by studying microlensing. That's when a massive object bends the light from a background star. In 2023, new data from the Subaru telescope in Hawaii hinted at strange lensing events that might be caused by planet-sized black holes passing in front of stars. It's not proof, but it's intriguing. The fact that these old animals may be linked to gravitational waves is another reason why scientists are interested in them. In 2015, the LIGO telescope picked up waves made when two black holes collided. Some of these black holes were much bigger than people thought they would be. This made me think of a crazy idea. What if they weren't from dead stars at all, but from the first black holes? There's also the possibility that these tiny black holes could evaporate. This idea comes from Stephen Hawking. He predicted that black holes aren't completely black. They slowly give off energy, a process now called Hawking radiation. Over time, a small black hole would shrink and heat up, eventually exploding in a final burst of energy. A primordial black hole could be bursting right now, shooting out a blast of gamma rays if it was small enough. These flashes are being looked for by spacecraft like NASA's Fermi Gamma Ray Space Telescope. We haven't seen anything solid yet, but the search is still going on. Some people even think that primordial black holes could help explain the strange fast radio blasts, or FRBs. These short bursts of strong radio waves come from galaxies that are billions of light years away. Some scientists think it could be because a neutron star broke apart and turned into a black hole, or because a small black hole ate a chunk of matter. What if a primordial black hole hit Earth? If it were tiny, say the mass of a mountain, but the size of a baseball, it would punch straight through. You probably wouldn't see it, but you might feel it. It could cause a shockwave, trigger earthquakes, or leave a tunnel of damaged atoms in its wake. In one theory, it could pass through the planet in seconds, loop around the sun, and come back again and again, eating away at Earth's mass little by little. Einstein rings and gravitational lensing, warping space itself. Think about looking at the stars through a huge magnifying glass. But instead of glass, it's gravity that's moving it. A process known as gravity lensing makes that happen. And when it all comes together just right, it makes an Einstein ring, a circle of light in the sky that looks almost too good to be true. gravitational lensing is real, not science fiction. It happens because mass bends space. This is what Albert Einstein predicted with his theory of general relativity. He said that anything with mass, like stars, planets, and black holes, can warp the space around it. And when light travels through that warped space, it bends too. So if you have a very massive object, say a galaxy or a black hole, and there's a more distant object behind it, like a faraway galaxy or a quasar, the light from that distant object doesn't travel in a straight line. It bends around the nearer object. From Earth, it looks like the distant object is in a different place, or like it has been duplicated or stretched into a ring. This is where Einstein rings come in. When everything is lined up just right, the light source, the lensing mass, and Earth, you get a full circular ring of light. It's like a cosmic halo. These rings are rare, but they're incredibly powerful tools for science. One famous example is Einstein Cross, where one distant quasar appears 4 times in the sky because a galaxy in front of it bends the light in multiple directions. Another, called SDSS J01460929, is a near-perfect ring formed by light from a distant galaxy warped by a closer galaxy cluster. These glowing circles aren't just pretty, they tell us a lot. First, gravitational lensing lets us see the invisible. Sometimes, the thing doing the lensing is full of dark matter, stuff that doesn't shine or glow, but still has mass. We can't see dark matter directly, but when its gravity bends light, we know it's there. In fact, lensing has been one of the strongest pieces of evidence that dark matter exists. Second, it magnifies distant objects. Galaxies that are too far and faint to see with normal telescopes can suddenly become visible when their light is bent and boosted by lensing. This has helped scientists discover some of the earliest galaxies in the universe, tiny smudges of light from just a few 100 million years after the Big Bang. In 2023, the James Webb Space Telescope used gravitational lensing to spot some of the youngest and most distant galaxies ever observed. Thanks to the natural magnification caused by massive galaxy clusters, scientists were able to study galaxies that would otherwise be invisible. It's like nature built its own telescope for us. But lensing does more than just show us galaxies far away. Einstein's idea can be put to the test. Einstein said that light would bend in a certain way. If this didn't happen, it would mean that our understanding of gravity is wrong. So far, Einstein's theory has held up. Even after 100 years, gravitational lensing fits his math almost perfectly. Even black holes can create Einstein rings. A black hole, especially a supermassive one, bends light so strongly that it can wrap the light completely around itself. If the source is directly behind it, we might see a complete circle of light around what seems like a hole in the sky. That eerie ring is called a photon ring, or sometimes even the shadow of a black hole. This is exactly what scientists captured in 2019 and again in 2022, when the Event Horizon Telescope produced images of black holes in the center of galaxies. Those glowing donuts of light are the real-world results of gravitational bending at its most extreme. There's also something called weak lensing. Instead of creating big obvious rings, it just slightly distorts the shape of background galaxies. By studying how millions of galaxies are subtly stretched in similar directions, scientists can map the dark matter structure of the entire universe. It's like seeing wind patterns by watching how leaves blow. Gravitational lensing also plays a role in solving other space mysteries. For example, it helped scientists study the Bullet Cluster, a pair of colliding galaxy clusters. The visible matter and the dark matter got separated during the crash. We couldn't see the dark matter, but lensing showed where it had gone, proving that it exists and behaves differently from normal matter. Lensing could help find rogue black holes, which are black holes that are not connected to any star. This is even more interesting. This is the only way we can tell if something moves in front of a star and quickly bends its light. Vacuum decay, a potential universe-killing event. Things feel safe at the moment. The stars are bright, atoms stay put. It looks like space is quiet. What if, though, every star, every planet, and every law of physics is built on a wrong base? It's possible that the world we live in is not in its lowest and healthiest state. Instead, it might be in a cosmic trap. That's what makes vacuum decay so scary. To understand vacuum decay, we first need to talk about fields, especially the Higgs field. This invisible field stretches across the entire universe. It's responsible for giving particles their mass. The famous Higgs boson, discovered in 2012 at CERN, is the fingerprint of that field. But here's the catch. Physicists don't know for sure if the Higgs field is in its true lowest energy state. If it's not, then it's in what scientists call a false vacuum. Think of a ball resting in a valley. It looks stable, but maybe there's a deeper valley nearby that's hard to see. If the ball ever gets nudged over the edge, it could fall into that lower valley. That's the idea behind vacuum decay. Our universe might seem stable, but there could be a deeper, more true version of space just waiting to be triggered. And if that happens, everything changes. If the Higgs field suddenly drops into its true lowest energy state, it wouldn't just stay in one place. The change would spread outward at the speed of light, forming a bubble of death, a growing sphere where the laws of physics are different. Inside that bubble, atoms might not even exist. The forces that hold particles together could break. Stars, planets, and people would be instantly erased. Not burned, not crushed, just unmade. And the worst part, you'd never see it coming. Because it moves at light speed, the bubble would hit you at the same instant you learned it existed. Some people might think this is crazy science fiction, but scientists really care about it. Some studies show that our universe might really be metastable, which means it is balanced in a false vacuum and ready to fall. This is based on the mass of the Higgs boson, which is about 125 giga-electron volts. Using what we know about the top quark and the Higgs boson, experts at CERN and other labs did the math in 2013. Their models showed that it is possible for vacuums to break down. It's not likely to happen soon, but it's also not impossible. Worse even, not much would have to happen to set it off. The decay could be started by a very small disturbance, or even a clash of particles with energies that are hard to imagine. This kind of thing could have happened on its own in the early world. Thank goodness it didn't. Or maybe we haven't seen it yet. A vacuum decay bubble that started very far away might already be on its way to us. We wouldn't be able to see it coming because it would be moving at the speed of light. For a moment, everything is okay. Following this, the physics rules change and erase reality. Could a human-made experiment start a vacuum decay? That's unlikely. The energies produced in even our most powerful machines, like the Large Hadron Collider, are tiny compared to those in natural cosmic events. Space is full of ultra-high energy cosmic rays that strike with much more force than anything we've built. If one of those hasn't triggered a decay yet, our machines probably won't either. But we're still learning. New physics, like theories involving extra dimensions, could change the rules. Maybe there are hidden variables we don't understand. Some theories suggest that vacuum decay could even happen more easily in the presence of black holes, which focus energy and warp space. There's also the idea that vacuum decay is inevitable, just extremely slow. Over trillions of years, the probability increases. In the far future, long after the last stars have died, a vacuum decay could wipe out everything that remains. In this version, the universe doesn't freeze, collapse, or fade. It pops. This possibility raises deep questions. Why is the universe metastable in the first place? Could something or someone have tuned the constants to make sure it holds together just long enough? Is vacuum decay a feature, not a bug? For now, we don't know. All we can do is measure, test, and calculate. Some researchers are trying to study the Higgs field more deeply, hoping to uncover whether it's truly stable. Others look at faraway galaxies and quasars, searching for signs that the laws of physics have changed somewhere else. If they have, it might be evidence that vacuum decay has already started somewhere. The most powerful signal we've ever received from space. Most of the signs we pick up in space are weak, repeated, and easy to understand. Pulsars beat like clocks in space. From faraway planets, quasars make noise. We do get some things that make scientists sit up straight every once in a while, though. A single burst, a jolt, or a signal that is so strong, quick, and strange that it doesn't seem to follow the rules. That's what happened with the strongest messages from space we've ever received, the WOW signal. On August 15th, 1977, a radio telescope at Ohio State University picked up something strange. A sudden burst of radio waves, 72 seconds long, screamed through the system. It came from the Sagittarius constellation in a frequency band that's quiet and reserved for space studies. The signal was so clean, so strong, and so unusual that astronomer Jerry Amon circled it on the computer printout and scribbled the word WOW next to it. To this day, nobody knows what caused it. It wasn't repeated. It wasn't from a known object. It came and went. No human satellite was near the location. And the signal was at 1420 megahertz, a frequency naturally emitted by hydrogen, the most common element in the universe. Some scientists believe that if aliens ever tried to contact us, they'd likely use that frequency. After all, it's the cosmic dial tone. The WOW signal has never returned, but it's not the only powerful mystery we've heard. In 2007, astronomers detected something even more intense, a fast radio burst, or FRB. These are bursts of radio waves that last only milliseconds, but they carry more energy than the sun produces in days. The first was caught accidentally by a radio telescope in Australia, and it was so powerful, some scientists thought it had to be a glitch. But over time, more were found. Some are one-off events. Others repeat like cosmic beacons with no known source. The brightest one ever recorded, FRB 202206110A, was so powerful that scientists estimate it released as much energy in 1,000th of a second as our sun emits in 30 years. And it came from billions of light years away. It's like a mosquito speaking in your ear from the other side of the world to give you an idea. So where do these messages come from? There's no way to be sure. Some scientists think FRBs might come from magnetars, neutron stars with incredibly strong magnetic fields. These stars can release bursts of energy when their magnetic fields shift or crack, like a cosmic earthquake. Others think they might be related to black holes, stellar mergers, or even alien technology. Yes, seriously. One Harvard professor, Avi Loeb, has suggested that some FRBs could be artificial, possibly the byproduct of propulsion systems used by alien spacecraft. However, most people don't see it that way. This is because FRBs are unexpected and only last a short time. And FRBs aren't the only strong signs we've seen. Neutron stars can also go wrong. These are rapid changes in how fast pulsars, which are spinning neutron stars that usually keep going like lights, spin. Pulsars will jolt every once in a while for reasons we don't fully understand. They will spin faster and release a burst of energy. These glitches don't happen very often and are hard to spot, but when they do, they quickly release a lot of energy that can shake the star's crust and maybe even send out gravity waves. The X-ray and gamma-ray bursts we've caught that appear without warning. Some come from sources we know, like black holes or collapsing stars. Others don't. In 2020, astronomers caught an extremely powerful X-ray burst from a magnetar in our own galaxy, and for a moment, it overwhelmed every X-ray detector on Earth. The burst lasted just milliseconds, but was so bright that, had it been much closer, it might have fried satellites or blinded telescopes. It's possible that gravitational waves, not electromagnetic energy, send the most strange messages. LIGO found the first ripple in space-time that was caused by two black holes merging in 2015. The signal was weak but strong. It moved space by a very small amount, about the width of a proton. That might not sound like much, but it meant that more than 1 billion years ago, two very large black holes slammed into each other, releasing the energy of 3 suns in a single moment. And just think, everything you've seen so far might only scratch the surface. Out there, beyond the veil of light and time, lie forces we haven't even discovered yet, Cosmic titans waiting to shake our understanding of reality all over again. If this journey through the universe's most powerful wonders left you awestruck, don't stop here. Like the video, drop your wildest space theory in the comments, and subscribe to Beyond Horizons so you never miss the next mind-bending dive into the unknown. The cosmos is just getting started.